Hello there and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight's gentle journey is all about one of the quietest forces in nature, a force with a name that sounds almost apologetic, but a role so important that stars, atoms, and even the story of matter itself would not be the same without it. We're talking about the weak force. And yes, calling it weak does feel a little unfair, a bit like calling the ocean damp or calling a black hole mildly clingy. The weak force may not push and pull in the obvious way that gravity does. It may not hold atoms together as dramatically as the strong force. It may not light up your room like electromagnetism. But it does something stranger. It changes particles. That is the part that makes it feel almost magical at first. Most forces, at least the ones we meet in daily life, seem to move things around. Gravity pulls a falling apple toward the ground. Magnetism tugs at a compass needle. Electricity makes a tiny shock leap from a doorknob after you walk across a carpet, which is rude but educational. The weak force is different. It can reach into the identity of a particle and alter what it is. A particle that began as one kind can become another kind. A neutron can turn into a proton. An electron can appear. A neutrino can slip away almost without leaving a trace, like a very polite ghost who has decided not to disturb the furniture. So before we go any deeper into this small and hidden machinery of the universe, let me ask you something gently. Where are you listening from tonight? Is it late where you are, with the room quiet and the world settling down? Or is it still early, perhaps with daylight at the window and a cup of something warm nearby? It is always a little comforting to think of people arriving here from different places, different clocks, different little corners of the same universe, all pausing for a while to wonder how matter changes when nature whispers to itself at its smallest scale. And if you find this soothing, interesting, or simply a peaceful way to let the day loosen its grip, I would be very grateful if you gave the video a like and maybe subscribed. It helps this calm little place reach others who might enjoy drifting through science without hurry, without noise, and without anyone suddenly shouting about breaking news from the quantum realm. The weak force is already surprising enough. We do not need jump scares from subatomic particles. Now, settle in. Let your thoughts slow a little. Let the words move at a gentle pace. Because tonight, we're not going to rush into the heart of the atom as if we're late for a train. We're going to arrive carefully. We will begin with the simple idea that particles are not always as permanent as they look. The universe is full of things that seem solid and steady from a distance, but when we look closely, we find tiny changes happening all the time. Matter is not just made, it is remade. It is adjusted, transformed, rearranged. And the weak force is one of the great reasons why. At first, the phrase weak force may sound small, almost harmless. It sounds like something that might gently nudge a dust mote across a shelf. But in physics, names can be a little misleading. The weak force is called weak because, over ordinary distances, it is much less powerful than the strong nuclear force in electromagnetism. It also works only across an extremely tiny range, far smaller than an atom. If gravity is the quiet pull that reaches across planets and stars, and electromagnetism is the lively force that fills rooms with light and holds chemistry together, then the weak force is more like a hidden switch inside matter, tucked away so deeply that we only notice its work after something has already changed. That hidden switch matters enormously. The weak force is responsible for certain kinds of radioactive decay. It helps explain how unstable particles transform. It plays a key role in the reactions that allow the sun to shine. It is involved with neutrinos, those nearly invisible particles that pass through planets, people, walls, and probably your pillow as you listen, without asking permission. In fact, every second, vast numbers of neutrinos from the sun pass through your body. You do not feel them, of course. If you did, bedtime would be much more complicated. But their existence is part of this deeper story, the story of a universe where change is built into matter at the most intimate level. Think for a moment about the world around you. A table feels like a table. A stone feels like a stone. Your hands feel like your hands. Everything seems to have a stable identity, and for the most part that is a very useful way to live. You do not need to wonder whether your spoon will suddenly become a fork halfway through breakfast. That would be inconvenient, especially if soup is involved. But at the level of particles, identity is more flexible. Some particles are stable, others are restless. Some can decay into lighter particles. Some can transform when the conditions are right. The weak force is one of the rules that decides how these changes happen. This is not change in the ordinary sense. A log burning into ash is a chemical change. Water freezing into ice is a change of state. Bread becoming toast is a breakfast decision with consequences. But when the weak force acts, it can change the very type of particle involved. It reaches beneath chemistry, beneath molecules, beneath atoms, into the smaller world of quarks and leptons. These are some of the basic ingredients of matter. Quarks make up protons and neutrons. Leptons include electrons and neutrinos. The weak force can allow one kind of quark to become another kind. And when that happens inside a neutron, the neutron may become a proton, while other particles are released. That little transformation sounds modest, but it is one of the most important processes in the universe. It is happening in radioactive materials. It happened in the early universe as matter took shape. It happens in stars. It is part of why the sun can turn hydrogen into helium and release the light that warms our planet. The weak force, in other words, is hidden inside the sunrise. Not in the golden glow itself, which belongs more directly to light and heat, but deep in the chain of events that allows the sun to keep shining at all. It is there in the slow patience of stars, in the ancient processes that forge the conditions for life, in the quiet background of existence. One of the odd things about the weak force is that it can feel less familiar than the other forces. Gravity is easy to notice. You drop something and it falls. Electromagnetism is everywhere, in light, electricity, magnets, chemistry, touch, and the little spark that sometimes jumps from your jumper in winter. The strong force is less visible, but we can understand its basic role. It binds the nuclei of atoms together. It helps hold protons and neutrons in place, despite the fact that protons, being positively charged, would otherwise prefer not to sit quite so close to one another. But the weak force does not announce itself in the same way. It does not hold your chair together. It does not keep your feet on the floor. It waits in the deeper background, acting when a particle is unstable enough, or when a nuclear process requires that one particle become another. In a way, the weak force is the force of permission. It permits certain transformations that would otherwise be impossible. It allows matter to find new arrangements. It opens doors between particle identities. But those doors are not wide open. They are narrow, rare, and governed by strict rules. A particle cannot simply become anything it likes. Nature is not running a costume party inside the atom. The weak force follows precise patterns. It respects conservation laws, balances charges, and produces particles in ways that preserve the deeper accounting of the universe. Even in change, nature is careful. This carefulness is one reason the weak force is so fascinating. It does not behave like a chaotic trickster. It is strange, yes, but not random in the ordinary sense. It has structure. It has messengers. In modern physics, forces are described through particles that carry interactions. Electromagnetism has photons. The strong force has gluons. The weak force has heavy carrier particles with short lives and serious responsibilities. Their heaviness is part of why the weak force works only over such tiny distances. They appear and vanish within the small allowed space of quantum interaction, doing their work before ordinary experience could ever notice. And that brings us to one of the great surprises of 20th century physics. The forces of nature are not all separate in the deepest way. At high enough energies, electromagnetism and the weak force reveal that they are connected, two faces of a more unified interaction. In our cool everyday universe, they look very different. Light can travel across galaxies. the weak force barely reaches across a fraction of a proton. But in the hot early universe, when everything was packed with unimaginable energy, these forces were once part of a single electro-weak story. As the universe cooled, the forces separated into the forms we know now, so even the weak force carries a memory of the early universe, a time when nature's rules were arranged differently, before matter settled into the familiar patterns that eventually led to stars, planets, oceans, and someone lying quietly in bed wondering why particles change. There is also something deeply strange about the weak force's preferences. Most of nature seems balanced in ways we might expect. Left and right often look interchangeable. A mirror reflection usually feels like a reversed but valid version of reality. Raise your left hand in a mirror, and the reflection raises what looks like it's right. Nothing too alarming there, but the weak force has a preference. It treats certain left-handed and right-handed particle states differently. This was a shocking discovery because it suggested that nature at its smallest level is not perfectly mirror-symmetric. The weak force has a kind of handedness. It cares about orientation in a way that feels almost personal, as if the universe looked in a mirror and quietly said, "Actually no, I prefer the other one." That preference has enormous consequences. It is one of the clues that the universe is not as simple or symmetrical as we might have guessed, and it may be connected, in ways scientists are still exploring, to the deep question of why matter exists in such abundance, while antimatter does not. In the early universe, matter and antimatter should have been produced in nearly equal amounts. If they had remained perfectly balanced, they might have destroyed one another, leaving behind mostly radiation and very little of the material world. Yet here we are, made of matter, sitting on a planet made of matter, orbiting a star made of matter, perhaps drinking tea made of matter, assuming you have not finished it already. Somewhere in the early history of the cosmos, nature leaned just slightly toward matter. The weak force is part of the physics that shows us such leanings are possible. The weak force also teaches us that instability is not failure. In ordinary language, unstable often sounds bad. An unstable chair is not something you want to discover halfway through sitting down. An unstable schedule can ruin a perfectly good afternoon. But in particle physics, instability can be creative. It is how heavier particles decay into lighter ones. It is how radioactive atoms transform. It is how processes unfold that would otherwise remain locked. Without this capacity for change, the universe would be colder, simpler, and far less interesting. Stability gives matter structure, but instability gives matter history. A neutron by itself, outside the safety of an atomic nucleus, does not last forever. It decays. Through the weak force, it can become a proton, releasing an electron and an anti-neutrino. That is one of the classic examples of weak interaction. But inside certain nuclei, neutrons can remain stable because the larger structure changes what is energetically possible. This is another reminder that particles do not exist in isolation from their context. The environment matters, the arrangement matters, the balance of energy matters. A particle that changes freely in one situation may remain steady in another. The universe is not just a list of ingredients, it is a set of relationships. And perhaps that is why the weak force feels so different from what we usually imagine when we hear the word force. It is not a shove. It is not a pull. It is a relationship that allows transformation. It is nature's way of saying that identity at the smallest scale is not always fixed. That does not mean anything can become anything. A proton will not become a pumpkin, no matter how festive the universe is feeling. But it does mean that the basic particles we use to describe matter are connected through rules of change. The weak force maps some of those connections. It shows us the quiet corridors between particle types. As we move through this story, we will meet several ideas that may sound strange at first. We will talk about quarks, the tiny constituents inside protons and neutrons. We will talk about leptons, including electrons and neutrinos. We will talk about decay, not as a gloomy ending, but as a transformation. We will meet the heavy messengers of the weak force, whose brief appearances make particle change possible. We will wander into the sun, carefully and only in imagination, where the weak force helps begin the long chain of reactions that send sunlight across space. We will explore why the weak force seems to care about left and right, and why that discovery made physicists sit up a little straighter in their chairs, or perhaps spill their coffee, depending on the physicist. But before all that, it helps to sit with the basic wonder. Matter changes, not just in the large visible ways of weather, erosion, growth, aging and cooling cups of tea, but in the tiny hidden ways that make the universe possible. Deep inside the atom, particles are not always locked forever into one identity. There are processes by which one becomes another, and the weak force is the guide through those processes. It is not loud. It is not long-ranged. It does not build mountains or make lightning flash across a sky. But it does something quieter and perhaps more profound. It lets the universe move from one particle arrangement to another. Imagine a library where most of the books stay on their shelves for years, steady and familiar. Gravity is like the floor holding up the building. Electromagnetism is like the light that lets you read. The strong force is like the binding that keeps the pages together. The weak force is the rare librarian who quietly replaces one book with another when the deeper story requires it. Most of the time, you do not see it happen. You only notice later that the shelf has changed. A neutron has become a proton. A neutrino has escaped. A nucleus has shifted into a new form. The library is still orderly, but it is not frozen. This is why the weak force matters so much to the story of physics. It reminds us that the smallest things are not merely tiny versions of everyday objects. A particle is not just a miniature marble with a label stuck to it. It is part of a system of fields, probabilities, interactions, and transformations. The weak force belongs to this deeper world, where the names we give things are useful but not final, and where change can happen without anything looking like it moved from one place to another in the ordinary sense. A particle changes because the rules allow it, because the interaction connects one state to another, because the universe has more subtle machinery than our senses were built to notice. And still, somehow, all of this hidden machinery leads back to the familiar world. The light on your wall began in nuclear processes. The warmth on your skin depends on stars. The elements in your body were shaped by cosmic histories that involve forces working at scales far beyond direct human feeling. The weak force is part of the reason those histories unfolded as they did. It is part of why particles changed in the early universe, why stars behave as they do, why certain atoms decay, and why ghostly neutrinos are constantly passing through the darkness. It is small in range, but enormous in consequence. So as we begin, try not to think of weak as meaning unimportant. Think of it instead as quiet. The weak force is quiet in the way roots are quiet beneath a forest. It is quiet in the way a clock mechanism is quiet behind the face. It is quiet in the way sleep arrives, not by pushing open the door, but by dimming the room one thought at a time. The weak force does not need to be loud to matter. It changes the universe from within. And the first step toward understanding it is to look closely at the particles themselves, those tiny inhabitants of matter that seem stable from a distance, but turn out to have their own patterns of restlessness, transformation, and surprising identity. Because before we can understand how the weak force changes particles, we need to understand why particles are able to change at all, and what kind of universe allows its smallest building blocks to quietly become something new. To understand the weak force, it helps to begin with one of the strangest facts in all of physics. The universe is not built only from things that sit still and remain what they are forever. It is also built from changes so small, so quick, and so deeply hidden that no human eye could ever watch them directly. These changes do not look like a falling stone or a spinning planet or a wave moving across a pond. They are not the familiar changes of weather rust, fire, or footsteps in the snow. They happen far beneath all of that, inside the private world of particles where identity itself can shift. In everyday life, we're used to objects keeping their names. A chair remains a chair, a spoon remains a spoon, a sleeping cat remains a sleeping cat, though perhaps one with strong opinions about being disturbed. If something changes, it usually changes because its pieces are rearranged. Wood burns because its molecules react with oxygen. Ice melts because water molecules move more freely. A metal gate rusts because atoms on its surface form new chemical bonds. These are changes in arrangement. The ingredients remain familiar, even when the form changes. But the weak force deals with a deeper kind of change. It is not merely rearranging atoms. It is not simply moving particles from one place to another. It can allow one kind of particle to become another kind of particle. That is a very different idea. It is as though, at the smallest scale, nature has a hidden set of doors between identities. Most of the time, those doors stay closed. Matter behaves steadily. Atoms keep their structures. The world looks dependable enough to make breakfast and trust the floor. But under the right conditions, one of those tiny doors opens, and a particle steps through as something else. This is why the weak force matters so much. It is not just a force of motion. It is a force of transformation. Gravity tells masses how to fall toward one another. Electromagnetism tells charged particles how to attract, repel, shine, bond, and spark. The strong force holds quarks together inside protons and neutrons and helps bind atomic nuclei. The weak force does something quieter and more surprising. It changes the flavour of particles. Flavour here does not mean strawberry, vanilla, or whatever suspicious flavour a medicine claims to be. In particle physics, flavour is a name for the kind or type of certain particles, especially quarks and leptons. It is one of those terms that sounds oddly casual for something so fundamental, as if the universe has a pantry. Let us begin with quarks. Protons and neutrons, the particles at the centre of atoms, are made of quarks. A proton is made from a particular combination of quarks, and a neutron is made from a slightly different combination. The difference between them is small but important. A proton has positive electric charge. A neutron has no overall electric charge. This difference shapes the structure of atoms and the behaviour of atomic nuclei. It helps determine what element an atom is. Change the number of protons in a nucleus, and you change the element itself. That is not a small edit. That is nature changing the title on the cover. The weak force can make this kind of change possible, because it can transform one type of quark into another. In one of the most famous examples, a down quark can become an up quark. When that happens inside a neutron, the neutron can become a proton. Along with that transformation, other particles are produced, including an electron and an anti-neutrino. This process is known as a form of radioactive decay. It is one of the clearest ways we see the weak force at work. Now, it is worth slowing down here, because this idea is easy to say but difficult to truly feel. A neutron is not simply cracked open like a nut with little pieces falling out in a simple mechanical way. The change is not like a tiny machine part being swapped by an even tinier mechanic with a toolbox. The particle is better understood through fields and interactions. The weak force allows a change in the underlying particle state. The neutron becomes a proton because one of its quarks changes identity. Then, to balance everything nature insists on balancing, other particles appear and carry away charge, energy, and other necessary properties. The universe does not let the bookkeeping slide. Even in its strangest moments, it keeps careful accounts. This is one of the remarkable things about particle physics. At first, it can sound wild, as if particles are doing anything they like. But the deeper truth is almost the opposite. Particle transformations are governed by strict rules. They can be surprising without being careless. A particle cannot simply become a different particle for no reason. The transformation has to be allowed by the laws of nature. Charges must balance. energy must be accounted for. Momentum, spin, and other properties must fit together in the final result. The weak force opens certain doors, but not all doors. Nature is imaginative, but not messy. When we say the weak force changes particles, we should also understand that it does not do so in a loud or constant way. If every particle changed identity all the time, the universe would be hopelessly unstable. Atoms would not hold together. Chemistry would lose its footing. You would not be able to read a label, let alone trust that the label still referred to the same object a moment later. Thankfully, many particles are stable, or effectively stable under ordinary conditions. The electron, for example, appears to be stable. The proton also appears to be extremely stable, at least for any timescale that matters to ordinary life. Matter has enough steadiness to build worlds, but steadiness is not the whole story. Some particles are unstable. They exist for a while, then decay. Some exist for only tiny fractions of a second before transforming into other particles. In particle accelerators, physicists can create heavy, short-lived particles that vanish almost immediately, leaving behind trails of lighter particles. Those trails are not failures of observation. They are the evidence. They are the footprints in the snow after the animal has already passed. The weak force is responsible for many of these transformations. It is the reason certain particles can decay into other particles that are not simply smaller pieces of themselves. This is different from breaking a vase. If a vase falls and shatters, the pieces are still ceramic. But when a particle decays through the weak force, the products can be different kinds of particles entirely. A muon, which is a heavier cousin of the electron, can decay into an electron, a neutrino, and an antineutrino. That does not mean the muon was secretly made of an electron and two neutrinos in the same way a sandwich is made of bread and filling. It means that the muon is an unstable excitation of a field, and through the weak interaction, it can transform into other excitations of other fields. That may sound less homely than a sandwich, but it is closer to the way modern physics describes the deep structure of reality. The word decay can make all of this sound gloomy, as if particles are wearing out. But particle decay is not really aging in the ordinary sense. A neutron does not decay because it is tired. A muon does not look at the clock and decide it has had a long day. Decay is a quantum process. It is governed by probabilities. For a single unstable particle, we cannot usually predict the exact moment it will decay. We can only say how likely it is to happen over time. With a large collection of identical unstable particles, the pattern becomes predictable. Some decay quickly. Some last longer. Together they follow a statistical rhythm, like raindrops beginning to fall on a roof. You may not know which drop will land next, but you can hear the storm building. This probabilistic nature is part of why the small world feels so different from the large one. A clock on a wall appears to tick in a regular way. A car moves along a road in a path we can track. A thrown ball follows an arc we can estimate. But an unstable particle carries a kind of uncertainty in its future. It has a chance of changing, and the weak force is part of the mechanism by which that chance becomes an event. The universe at this scale is not chaotic, but it is not clockwork in the simple old sense either. It is rule-governed probability. One of the smallest transformations in the universe can therefore reshape something much larger. When a neutron becomes a proton inside a nucleus, the identity of the atom may change. Imagine an atom with a certain number of protons. That number defines what element it is. If a neutron in the nucleus changes into a proton, the nucleus now has one more proton than before. It may become a different element. This is one of the ways radioactive decay can transform one element into another. Alchemy, in its old mystical dream, wanted to turn one substance into another, often leading to gold. The weak force does not work according to human wishes, and it is not concerned with treasure chests, but it does show that elements are not eternally fixed. Under the right nuclear conditions, nature can change one into another. This is especially important in the history of the universe. The elements did not all appear at once in their present abundance. In the early universe, in stars, in supernovae, and in other extreme environments, particles and nuclei transformed through nuclear reactions and decays. The weak force helped shape the balance of protons and neutrons. That balance mattered for which elements could form and in what quantities. A tiny interaction in the subatomic world influenced the chemical ingredients available for planets, oceans, rocks, and living things. It is a little humbling to realize that part of what makes your body possible depends on transformations too small to imagine and too ancient to remember. There is another quiet lesson here. The weak force reveals that matter is not just a static pile of building blocks. It is a set of possibilities constrained by laws. A neutron can be stable inside some nuclei and unstable on its own. A particle can decay if there is a lower energy path available and if the transformation is allowed. The same particle may behave differently depending on where it is and what surrounds it. Context matters even at the smallest scale. The universe is not merely made of things, it is made of things in relation. This is why the weak force can be difficult to picture. We are used to forces having visible effects. Push a door and it opens, pull a drawer and it slides, switch on a lamp and light fills the room. The weak force does not usually present itself like that. It is not experienced as a pressure on your hand or a glow in your eye. Its signs are indirect. A nucleus emits radiation. A detector records a particle track. A neutrino appears to have carried away missing energy. A star shines because a slow chain of nuclear processes is able to proceed. The weak force is known by what it permits, and what it permits is astonishing. Consider the sun. Its light feels familiar, almost ordinary, because we see it so often. Morning sunlight on a wall does not announce the complexity behind it. But deep in the solar core, hydrogen nuclei are involved in a chain of reactions that ultimately produces helium and releases energy. The first crucial step in the main chain requires the weak force. Two protons come together, and one of them must transform into a neutron for the process to continue. Without the weak force, that step would not happen in the same way. The sun would be a very different object. The gentle warmth that reaches Earth depends in part on one of the rarest and slowest subatomic transformations in the solar furnace. That slowness is important. If the weak force were much stronger in this process, stars like the sun might burn through their fuel far more quickly. If it were too weak, or behaved differently, the path to steady hydrogen fusion might be blocked or altered. The weakness of the weak force is not a flaw. It helps set the pace. It allows stars to shine steadily for billions of years, rather than exploding through their fuel like a candle in a hurricane. There is something almost restful about that. The weak force, quiet and limited as it is, helps give stars patience. The small transformations it governs also produce neutrinos. Neutrinos are among the most elusive particles we know. They interact so rarely with ordinary matter that they can pass through vast distances of solid material, almost as if nothing is there. Every second, solar neutrinos stream through Earth, through buildings, through oceans, through you, continuing onward as if our planet were a thin morning mist. They are born in processes involving the weak force, and they carry information from places light cannot easily escape, such as the deep interior of the sun. In that sense, the weak force sends out messengers from hidden rooms in the universe. The fact that neutrinos interact through the weak force is one reason they are so hard to detect. If they were governed by electromagnetism, they would be much easier to notice because they would interact with charged particles and light. But neutrinos have no electric charge, and they ignore the electromagnetic world almost completely. They are not pulled into the ordinary dance of chemistry and light. They take part in the weak interaction and gravity is so feeble for such tiny particles that it hardly helps us catch them. Detecting neutrinos requires enormous instruments and great patience. It is a bit like trying to hear one's soft footstep during a thunderstorm, except the footstep may pass straight through the floor. Still, those ghostly particles matter. Their existence helped solve a mystery in radioactive decay. Early physicists noticed that energy seemed to be missing in certain decay processes. Something unseen had to be carrying it away. The neutrino was proposed as a nearly invisible particle to preserve the careful accounting of nature. Later it was detected, confirming that the universe had indeed been balancing its books with an almost undetectable messenger. There is a gentle humour in that. Nature had not broken its own rules. It had simply hidden part of the receipt. These smallest transformations also reveal that the word particle can be slightly misleading. It tempts us to imagine tiny solid beads, but particles in modern physics are more like disturbances or excitations in underlying fields. An electron is not a little hard ball. A quark is not a grain of sand. A neutrino is not a microscopic speck drifting through space like dust. They are quantum objects with properties, probabilities, interactions, and possible transformations. The weak force acts within that quantum framework. It does not grab a particle with fingers and reshape it. It connects one possible state to another through the rules of the fields. This can feel abstract, but the results are concrete. Radioactive decay can be measured, neutrinos can be detected, nuclear reactions power stars, particle transformations can be observed in detectors. Medical imaging, nuclear dating, particle physics experiments, and astrophysics all depend in various ways on understanding these processes. The weak force may seem remote, but it is part of the working machinery behind technologies and observations that touch the human world. It is one of those hidden facts that quietly supports much of what we know. There is also a philosophical softness to this. The weak force tells us that identity in the universe is not always rigid. At the level of ordinary life, identity has continuity. You wake up as yourself. Your table remains your table. The moon remains the moon. But at the quantum level, certain identities are temporary arrangements. A particle can be itself for a while, then become something else according to the allowed patterns of nature. The universe contains both permanence and transition. It has stones and rivers, atoms and decays, stable particles and brief flashes that vanish almost as soon as they arrive. This mixture of stability and change is essential. Too much stability and nothing interesting happens. Too much change and nothing lasting can form. The world we know exists in the balance. Protons and electrons are stable enough to build atoms. Atoms are stable enough to build molecules. Molecules are stable enough to build cells, oceans, air, and late-night cups of tea. But instability still exists in the right places. Radioactive nuclei decay. Stars transform hydrogen into helium. Heavy particles produced in energetic events decay into lighter ones. The weak force helps maintain this balance between what remains and what changes. So when we speak of the smallest transformations in the universe, we're not talking about minor details. We're talking about the tiny acts of change that make the larger story possible. A quark changes flavor. A neutron becomes a proton. A neutrino slips away. A nucleus becomes a different nucleus. A star begins a reaction chain that will shine across space. Each step is small beyond imagination, yet together they shape cosmic history. It is strange to think that something so hidden can be so powerful in consequence. The weak force does not build mountains directly, but without the processes it allows, the material history of stars and elements would be different. It does not shine like light, but it helps begin the path by which sunlight is made. It does not hold your hand to the table or your feet to the ground, but it helps explain why matter has the forms and histories it does. It is the quiet permission behind transformation. And as we keep following this force inward, the next question naturally appears. Why do some particles change while others remain steady? What makes one particle stable, another short-lived, and another almost impossible to catch? To answer that, we need to look more closely at the restlessness built into the particle world, and at the strange fact that some particles seem almost unwilling to stay themselves for very long. Some particles seem perfectly content to remain themselves. They sit in the deep inventory of nature like reliable old furniture, familiar, sturdy, not especially dramatic, and absolutely necessary if you want a universe that can build anything more complicated than a brief flash of energy. Electrons appear to be stable. Protons appear to be stable for all practical purposes. Photons, the particles of light, can travel across the universe for billions of years, crossing dark stretches of space with the patience of a very dedicated postal service. These particles give the world a sense of continuity. They help make matter dependable. They are the reason atoms can last, chemistry can happen, and a cup can remain a cup long enough for you to misplace it. But not every particle is so settled. Some particles are more like guests who arrive late, stay for barely a moment, and leave before anyone has properly learned their name. Others last long enough to be measured, but not long enough to become part of ordinary matter. Many particles, especially heavier ones, are unstable. They do not stay themselves forever. They decay into lighter particles, often through the weak force, leaving behind a new arrangement of the universe and a set of clues for physicists to follow. This is one of the first things to understand about particle decay. It is not decay in the everyday sense of rotting fruit, crumbling wood, or a forgotten sandwich becoming a tiny biological civilization at the back of the fridge. A particle does not decay because it is old, tired, damaged, or poorly stored. It decays because the laws of physics allow it to transform into a different set of particles with lower energy, while still preserving all the necessary balances that nature insists on keeping. Charge must be balanced. Energy must be balanced. Momentum must be balanced. Other particle properties must also fit properly. If the transformation is allowed, and if there is a lighter state available, then an unstable particle may eventually take that path. The word may is important. At the quantum level, decay is not usually something we can predict for one single particle with perfect certainty. We can say that a certain type of particle has an average lifetime. We can say that if we have a large group of them, a predictable fraction will decay over a certain amount of time. But for one individual unstable particle, the exact moment of transformation is not fixed in the way a train timetable is supposed to be fixed, though trains themselves often seem to have entered quantum uncertainty for reasons unrelated to physics. One particle may decay quickly. Another identical particle may last longer. The pattern is reliable in crowds, but mysterious in individuals. This is not because we are missing a tiny clock hidden inside the particle. It is not sitting there with a countdown timer, waiting to ring. The uncertainty belongs to the structure of quantum theory itself. An unstable particle has a probability of decaying. That probability is connected to the interactions available to it. The weak force provides some of the most important routes by which particles can change. It does not push the particle in the way a hand pushes a door. Instead, it allows a transformation from one quantum state into another. The particle is not making a decision, of course. It is following the rules of a universe where possibilities have weight, and where some possibilities eventually become events. One reason some particles refuse to stay themselves is that they are heavy compared with the particles they can become. In particle physics, heavier often means carrying more energy. If a heavy particle can transform into a set of lighter particles while preserving nature's bookkeeping, then it is likely to be unstable. It has a way to lower its energy, like a marble rolling down a hill if the path is open. But this comparison can only take us so far because quantum particles are not little marbles, and decay is not a simple roll down a slope. Still, the basic idea is helpful. If a particle has a permitted route into a lighter arrangement, it usually will not remain forever. The muon is a good example. A muon is sometimes described as a heavier cousin of the electron. It has the same electric charge as the electron, but it is much more massive. It does not belong in ordinary atoms under normal conditions, and when muons are created, they do not last very long. Through the weak force, a muon can decay into an electron, along with a neutrino and an antineutrino. The electron remains, the neutrino and antineutrino slip away, and the muon is gone. It has not broken into pieces that were sitting inside it like raisins in a cake. Rather, the muon has transformed through an allowed weak interaction into a different set of particles. This is a subtle but important distinction. When we say a particle decays, our everyday imagination may picture something coming apart. We might picture a watch spring snapping, or a biscuit crumbling into crumbs. But many particle decays are not simple breakups. The particles that appear afterward were not necessarily hidden inside the original particle, in the ordinary sense. They are created in the transformation, as the original particle state gives way to new states. The weak force makes this creation possible according to the rules of conservation and probability. In this small realm, change is not just rearrangement, it is replacement. The tau particle is another example. It is like an even heavier relative of the electron and the muon. Because it is so heavy, it has many possible decay routes. It lives for an extremely short time and then transforms into lighter particles. It is almost as if nature says, "You may exist, but only briefly." The tau is real, measurable and important, but it is not part of the calm furniture of everyday matter. It belongs more to high-energy events, particle accelerators, and the early universe, where heavier particles can be made and then quickly vanish into lighter descendants. There are also unstable particles made of quarks, such as pions and kaons. These particles often appear in cosmic rays and accelerator experiments. Some decay through the weak force, producing particles that can reveal the rules of transformation. Kaons, in particular, played an important role in showing that nature is not perfectly symmetric in the way physicists once expected. Their decays helped reveal tiny differences between matter and antimatter behavior, clues that remain deeply important in the search to understand why our universe contains so much matter. Even the brief lives of particles can leave long shadows in science. So what separates the stable from the unstable? Why does an electron stay an electron while a muon does not? Why does a free neutron decay while a proton appears to endure? The answer lies in what transformations are available. An electron is the lightest particle with its electric charge. There is no lighter charge particle for it to become while preserving charge and the other required properties. It has nowhere lower to go. In that sense, the electron is like someone already sitting on the ground floor of a building with no basement. It cannot take the stairs down because there are no stairs. The proton is also stable as far as ordinary physics is concerned. It is the lightest baryon, a type of particle made from 3 quarks. A free proton has no allowed ordinary decay path into lighter particles that preserves all the necessary rules. Some grand theories beyond the standard model suggest that protons might decay over unimaginable timescales, but no one has observed this. For the world we live in, the proton is wonderfully dependable. It sits at the heart of hydrogen, helps define the elements, and forms much of the visible matter around us. If protons decayed easily, the universe would not be a place of durable atoms and quiet bedrooms. It would be a much less restful arrangement. A neutron is more complicated. Inside many atomic nuclei, neutrons can be stable because the structure of the nucleus makes decay energetically unfavourable or forbidden in that context. But a free neutron, outside the nucleus, is unstable. It can decay into a proton through the weak force, producing an electron and an antineutrino. This is one of the classic weak transformations. A down quark inside the neutron changes into an up quark, turning the neutron into a proton. The electron carries away negative charge, and the antineutrino carries away energy and other properties. The neutron has not merely fallen apart, it has changed identity through the weak interaction. This example also shows how context matters. A neutron by itself is unstable, but a neutron inside a nucleus may remain stable because the whole arrangement has different energy conditions. It is a little like a person who is restless alone but perfectly comfortable in the right room with the right company, though particles, to be clear, are not known for their social skills. Nuclear structure changes what can happen. Some nuclei have too many neutrons or too many protons to be stable. When the balance is off, The weak force can help the nucleus move toward a more stable arrangement by converting a neutron into a proton, or a proton into a neutron, depending on the situation. This is the basis of certain kinds of radioactive decay. In one case, a neutron becomes a proton and an electron is emitted. In another case, a proton can become a neutron with the emission of related particles, or by capturing an electron from close to the nucleus. These processes change the number of protons in the nucleus, and that means the element itself changes. A nucleus that began as one element can become another. The weak force, working through tiny particle transformations, can alter the chemical identity of matter. It is hard to imagine a smaller action with a larger consequence. When people first discovered radioactivity, they did not know this deeper explanation. They saw materials that emitted invisible rays, fogged photographic plates, and seemed to release energy from within themselves. It was mysterious, almost unsettling. Over time, scientists learned that radioactive decay came from changes in atomic nuclei. Later still, particle physics revealed the role of weak interactions in many of those changes. What began as a strange glow from certain minerals became a window into the deep rules by which particles transform. The weak force is especially important because it can change quark flavor. Quarks come in different types, and only certain combinations form the protons and neutrons we know so well. A proton and a neutron differ because of the quarks inside them. Change one quark in the right way, and you can change one particle into the other. This is not something the strong force does. The strong force binds quarks together, but it does not change one quark type into another. Electromagnetism acts on electric charge, but it does not turn a down quark into an up quark. Gravity acts on energy and mass, but it is far too weak at these scales to govern such transformations. The weak force has this special talent. It changes flavor. That word flavor may sound almost too charming for a force that governs radioactive decay and solar fusion, but it hints at something useful. Particles can share broad categories while differing in type. Up quarks and down quarks are both quarks, but they are not the same. Electrons, muons, and tau particles are all charged leptons, but they are not the same. Neutrinos also come in different types. The weak force is deeply involved in how these types interact and transform. It is part of the hidden grammar of particle identity. The existence of unstable particles also tells us that the universe has layers of reality we do not normally experience. Everyday matter is made mostly from up quarks, down quarks, electrons, and the force fields that bind and connect them. That is the stable, low-energy world we inhabit. But particle accelerators and cosmic rays reveal heavier cousins and more exotic combinations. These particles are not normally present in the quiet matter of chairs, rocks, and sleeping cats. They appear when enough energy is concentrated into a tiny region, and then they decay rapidly. It is as if high energy opens a temporary attic in nature's house, full of strange old objects that cannot remain downstairs for long. The early universe was full of such high-energy conditions. In its first moments, the universe was hot and dense beyond ordinary imagination. Heavy particles could form easily, interact, and decay. As the universe expanded and cooled, many unstable particles vanished into lighter, more stable ones. The matter we see today is what survived this long cooling and sorting process. The weak force was part of that sorting. It helped determine which particles transformed, how quickly, and into what. The calm stability of the modern universe is, in a sense, the result of ancient instability having worked itself out. This is one of the reasons unstable particles are not just scientific curiosities. Their decays are clues to the deep past. When physicists study how particles decay, they are not merely cataloguing odd behaviour. They are testing the laws that governed the early universe. They are asking whether the rules are exactly as our theories say, or whether tiny deviations point toward deeper physics. A rare decay, a slightly unexpected pattern, a missing particle, or a subtle imbalance between matter and antimatter can become a signpost. In particle physics, a brief event can carry the weight of a cosmic question. There is also a quiet lesson in how particles decay through different forces. Some decays happen through the strong force and are extremely fast. Some happen through electromagnetism and are also quick, though often less so. Weak decays are usually slower by comparison because the weak interaction is, well, weak and short-ranged. This difference in speed helps scientists identify what kind of interaction is responsible. A particle that lives slightly longer than expected at subatomic timescales may be lasting longer because it must decay through the weak force rather than through a stronger interaction. To us, these lifetimes are still unimaginably brief. To a particle physicist, the difference can be as meaningful as the difference between a blink and a century. The heaviness of the weak force carriers is part of this story. The weak interaction is carried by very massive particles, which makes it short-ranged and comparatively difficult to access. These carriers allow particles to exchange the necessary changes, including shifts in charge and flavour. Because the carriers are so heavy, the interaction does not reach far. It acts only within tiny distances. This is why the weak force is hidden from everyday experience. Its messengers do not travel across rooms like light. They appear in the small quantum exchange and vanish almost immediately, leaving the change particles behind. And yet, despite this tiny range, the weak force influences enormous things. It sets decay pathways, it helps power stars, it produces neutrinos, it shapes nuclear transformations, it participates in the balance between particle stability and particle change. A force does not need to reach across galaxies to matter. Sometimes a force changes the future by acting in a space smaller than an atom. It may help to think of unstable particles as holding a question inside them. Not a conscious question, of course, but a physical one. Is there an allowed way to become something lighter? If the answer is no, the particle remains stable. If the answer is yes, then decay can happen. The weak force provides many of the possible answers. It says, under these rules, with these balances preserved, this particle may become those particles. It is a language of permitted transformations. This is why particle physics often feels like studying a very strict but very strange grammar. There are nouns such as electrons, quarks, neutrinos, and muons. There are verbs such as decay, scatter, annihilate, and transform. There are rules about what can appear where, what must balance, and which processes are allowed. The weak force is one of the grammar rules that lets certain sentences be written. A neutron becomes a proton with an electron and an antineutrino. A muon becomes an electron with neutrinos. A heavy quark can become a lighter quark. These are not random phrases. They are valid sentences in the language of matter. Of course, this language can be difficult because it does not match ordinary intuition. We expect things to have clear boundaries. We expect cause and effect to feel visible. We expect objects to be made of parts that remain parts. Particle decay challenges all of that. It tells us that a thing can be unstable, not because something is wrong with it, but because its existence includes an allowed transformation. It tells us that the result of a decay is not simply hidden inside the beginning. It tells us that identity, energy, and interaction are tied together in a way our everyday senses never had to understand. Still, the universe built from these rules is the same universe that gives us ordinary calm. The stability of the electron, the endurance of the proton, the conditional stability of the neutron, and the brief lives of heavier particles all fit into one wider pattern. Some things last, some things change, some changes happen almost instantly, some take time, some are forbidden, some are rare but possible. From that mixture the world gets both structure and history. If every particle were stable, the universe might be dull and frozen in its earliest arrangements. If every particle were unstable, nothing lasting could form. The beauty is in the balance. Stable particles become the alphabet of matter. Unstable particles reveal the deeper grammar. The weak force is one of the ways the grammar moves. So when we ask why some particles refuse to stay themselves, the answer is not that they are faulty or impatient. It is that nature allows them a path. They carry enough energy to become something else. The weak force opens the door. The rules of conservation guide what can pass through. Quantum probability decides when the passing happens, and the result is a new set of particles, lighter, balanced, and woven into the continuing story of matter. This story now brings us closer to the kind of change that first made the weak force visible in the laboratory and in nature. Radioactive decay is not just a strange property of certain atoms. It is one of the clearest windows into the weak force at work. It shows how a tiny particle transformation inside a nucleus can change an atom, release radiation, and reveal that matter is not quite as fixed as it seems. Radioactive decay sounds at first like one of those phrases that belongs in warning signs, laboratory doors and old science fiction films where something glows in a suspiciously green way. It can sound dangerous, sharp, and distant from ordinary life. But underneath the drama of the word radioactive is a quieter idea. Some atoms are not completely settled. Their nuclei carry an arrangement of protons and neutrons that cannot remain steady forever. Sooner or later, through rules far beneath chemistry and far smaller than anything our senses can notice, they change. That change is radioactive decay, and one of the great secrets behind it is the weak force. Not all radioactive decay belongs to the weak force. Nature has more than one way for an unstable nucleus to release energy or move toward a better balance. Sometimes a heavy nucleus releases a compact cluster made of protons and neutrons. Sometimes an excited nucleus releases a burst of light with very high energy. But when a neutron becomes a proton, or a proton becomes a neutron, when the identity inside the nucleus changes rather than merely shifting pieces around, the weak force is at work. It is the small hidden mechanism that allows one particle type to turn into another, and by doing so it can change one element into another. That is worth sitting with for a moment. The identity of an element is defined by the number of protons in its nucleus. Hydrogen has 1 proton, helium has 2, carbon has 6, oxygen has 8, gold has 79, which is one of the reasons it has been so confident throughout human history. If the number of protons changes, the element changes. This means that a tiny event inside a nucleus, a single particle transformation governed by the weak force, can change the chemical identity of an atom. The atom becomes something else, not because its outer electrons are rearranged, not because it has joined a new molecule, but because the heart of the atom has altered. The heart of the atom, the nucleus, is a crowded place. It is made of protons and neutrons, packed into a region so small that ordinary comparisons begin to wobble. Protons carry positive charge, so they naturally repel one another through electromagnetism. The strong nuclear force holds them together at extremely short distances, gripping protons and neutrons tightly enough to form stable nuclei. But not every arrangement is equally comfortable. A nucleus can have too many neutrons or too many protons, or too much energy packed into its structure. It can be out of balance. And when that happens, radioactive decay becomes one of the ways nature rearranges the situation. The weak force is especially important when the imbalance involves the ratio of protons to neutrons. A nucleus with too many neutrons may become more stable if one neutron changes into a proton. A nucleus with too many protons may become more stable if one proton changes into a neutron. These changes are not chemical. They are not about the atom making a bond or losing an electron from its outer shell. They are nuclear. They happen in the compact core of the atom, where the strong force, electric charge, and weak force all help decide what is possible. The most familiar weak radioactive process is often called beta decay. In one kind of beta decay, a neutron changes into a proton. At the same time, an electron is emitted, along with a very elusive particle called an anti-neutrino. The electron is what early scientists first noticed as the beta particle. The antineutrino came later in the story, almost like a missing guest who had quietly been leaving through the back door all along. It was needed because the decay did not seem to balance properly without it. Energy and other properties appeared to be missing. Physicists eventually realized that something nearly invisible must be carrying them away. This is a beautiful example of how careful nature is. The decay looked messy at first. It seemed as though the accounting did not add up. But the problem was not that nature had broken its rules. The problem was that we had not yet found all the players. The antineutrino was proposed as a solution, a tiny neutral particle that could slip away with the missing energy. It was incredibly hard to detect because it interacts so rarely with matter. But eventually neutrinos and antineutrinos became real experimental facts, not just clever bookkeeping. The invisible receipt had been found. When a neutron becomes a proton through the weak force, we can look one layer deeper. Protons and neutrons are made of quarks. A neutron contains one arrangement of quarks. A proton contains a slightly different arrangement. In this weak transformation, one kind of quark inside the neutron changes into another kind. That quark change is what turns the neutron into a proton. The electron and antineutrino appear as part of the same process, carrying away the required charge, energy, and other properties. The change is tiny beyond imagination, but the result is clear. The nucleus now has one more proton than before, and because it has one more proton, the atom has become a different element. This is the quiet power of weak, radioactive decay. It can alter the periodic table from within. A nucleus that was one element can transform into the nucleus of another element. It is not magic, though it may sound like the kind of thing medieval alchemists would have been very interested in if they had been given a particle detector and a comfortable chair. It is physics. It is the weak interaction allowing a change in the identity of matter, while every conserved property is carefully balanced. There is another kind of weak decay that moves in the opposite direction. In a proton-rich nucleus, a proton can become a neutron. This can happen in a couple of related ways. In one, the nucleus emits a positively charged partner of the electron, known as a positron, along with a neutrino. In another, the nucleus captures one of its own inner electrons, and that capture helps turn a proton into a neutron while a neutrino is released. These processes also belong to the weak force because they involve changing one type of particle into another. Again, the key is transformation. The nucleus is not merely shaking off excess energy, it is changing its internal identity. This is why radioactive decay is not one single thing. It is a family of processes. Some involve the strong force and the structure of large nuclei. Some involve electromagnetic radiation from excited nuclei. Some involve the weak force and particle identity. The weak force does not explain every form of radioactivity, but it explains some of the most important and revealing forms, the ones where neutrons and protons trade places through changes in their quarks. Early radioactivity was discovered before anyone knew about protons, neutrons, quarks, neutrinos, or the weak force. At the end of the 19th century, scientists found that certain minerals seemed to give off invisible emissions. These emissions could pass through paper, fog photographic plates, and discharge electroscopes. It was strange and unexpected. Matter, which had seemed solid and quiet, was apparently releasing energy from deep within itself. It was as if a stone on a shelf had turned out to contain a tiny weather system. Over time, researchers learned that radioactive materials gave off different kinds of radiation. Some radiation could be stopped by paper, some could pass farther but be stopped by metal. Some was extremely penetrating. These different emissions were eventually understood as different processes. The picture became clearer as atomic structure was discovered. The atom was not indivisible. It had a nucleus. The nucleus could change, and those changes could release particles and energy. For a while, beta decay was especially puzzling. When scientists studied the emitted electrons, they found that the energy seemed spread over a range of values rather than fixed at one neat amount. If the nucleus simply changed into another nucleus and emitted one electron, the electron energy should have been more definite. Something was missing. This was a serious problem. Some even wondered whether energy conservation might fail inside beta decay. That would have been a very dramatic outcome, the sort of thing that makes physicists stare quietly at blackboards for a long time. Instead, the neutrino saved the day. The idea was that beta decay produced not 2 final objects, but 3. The new nucleus, the electron, and a neutral, nearly undetectable particle. The energy was shared among them. That is why the electron could come out with different energies. The missing energy was not missing at all. It had been carried away by a particle so ghostly that it barely touched the world. It is hard not to admire the neatness of that solution. Nature did not throw away energy. It just handed some of it to a particle that was very difficult to invite to an experiment. The neutrino will become more important as we continue, because it is one of the signature particles of weak interactions. It is produced in many weak processes, including beta decay and nuclear reactions in stars. It passes through matter with astonishing ease because it does not feel electromagnetism and does not participate in the strong force. It mainly interacts through the weak force, which is precisely why it is so difficult to catch. If particles had personalities, the neutrino would be the one quietly leaving a party before anyone noticed it had arrived. But let us stay a little longer with radioactive decay itself, because it tells us something important about time at the nuclear scale. A radioactive atom does not decay because it has become old in the everyday sense. It does not gather wrinkles. It does not weaken like a tired bridge. 2 identical unstable nuclei can sit side by side, and one may decay soon while the other remains unchanged for much longer. The exact moment is not predictable for a single nucleus. But if you have a huge number of identical radioactive nuclei, the overall pattern becomes very predictable. A certain fraction will decay in a given time, then a fraction of what remains will decay in the next interval, and so on. This is one of the strange balances of quantum physics. Individual events may be uncertain, but large groups can behave with remarkable regularity. Radioactive decay is random in the moment but orderly in the crowd. It is a little like popcorn in a pan. You cannot say exactly which kernel will pop next, but you can describe the overall popping pattern as the heat continues. Though unlike popcorn, radioactive atoms are not improved with butter. The rate at which a radioactive substance decays is described by its half-life, the time it takes for half of a sample to decay. Some half-lives are tiny fractions of a second, some are thousands of years, some are billions of years. This wide range exists because different nuclei have different structures and different possible decay pathways. If a decay route is easy and strongly allowed, it may happen quickly. If it is rare or difficult, it may take a very long time. The weak force often produces processes that are relatively slow by nuclear standards, and that slowness can matter enormously. In everyday life, radioactive decay can feel distant, but it has many practical uses. Some radioactive isotopes act as natural clocks. Carbon dating uses the decay of a radioactive form of carbon to estimate the ages of once-living materials. Other radioactive isotopes help date rocks and meteorites, allowing scientists to estimate the age of Earth and the solar system. In medicine, radioactive materials can be used in imaging and treatment. In nuclear power, the energy released by unstable nuclei is part of a much larger engineering story. All of these applications depend on the fact that radioactive decay follows reliable statistical laws. The individual atom may be unpredictable, but the population keeps time. There is a quiet irony here. Radioactive decay, which comes from uncertainty at the smallest scale, gives us some of the most dependable clocks for deep history. A single unstable nucleus is unpredictable. A mountain full of them can tell us about ages older than civilization, older than animals, older than the continents in their present form. The tiny randomness of the nucleus becomes a steady calendar when multiplied across matter. Nature is very good at turning small uncertainty into large-scale order. The weak force is part of that deep calendar. In beta decay, it sets the pathway by which certain nuclei transform. Those transformations leave behind daughter nuclei, emitted particles, and measurable changes in composition. When scientists read these changes, they are reading the record of nuclear time. A rock can carry within it the evidence of atoms slowly transforming over millions or billions of years. There is something almost peaceful about that, not in a mystical way, but in the plain scientific fact that matter keeps records. A mineral sits quietly in the dark, and inside it, rare tiny transformations mark the passing of deep time. Radioactive decay also matters because it changes the energy inside Earth. Some of the heat inside our planet comes from the decay of radioactive isotopes in rocks. That heat helps influence geological activity over immense spans of time. It contributes to the warmth of Earth's interior, which is connected to mantle movement, volcanism, and the long, restless life of the planet beneath our feet. The weak force is not the whole story of Earth's heat, and not all radioactive decay in Earth is weak decay, but weak processes are part of the family of nuclear changes that help shape planetary history. A force acting inside nuclei can, through many steps and much time, help warm a world. At the same time, radioactive decay reminds us that instability is not unusual in nature. It is built into certain arrangements of matter. A nucleus may be stable for a second, a year, 1,000 years, or longer than the age of the universe, depending on what it is and what transformations are available. Stability is not simply yes or no, it is a question of time scale. Something that seems perfectly stable in a human lifetime may be slowly changing on geological timescales. Something that appears in a particle accelerator may vanish before it can cross a distance smaller than a grain of dust. Nature has many clocks, and not all of them tick at human speed. The weak force gives some of those clocks their rhythm. Because weak interactions are short-ranged and involve heavy carrier particles, weak decays often happen more slowly than decays governed by stronger interactions. To us, even a weak decay of a particle may be incredibly fast, but to the particle world, these differences are meaningful. A particle that must decay through the weak force may live long enough to travel a measurable distance in a detector before transforming. That tiny delay can be a clue. It can tell physicists what kind of process occurred. In experiments, the lifetime of a particle is part of its fingerprint. You can see how radioactive decay becomes a kind of detective story. Something changes, a particle appears, energy is carried away. A detector records a track, a flash, or a signal. Scientists reconstruct what happened. Did a neutron become a proton? Did a proton become a neutron? Was a neutrino produced? Was an electron emitted? What balances were preserved? What pathway was allowed? The weak force is not seen directly like a tiny lever being pulled. It is inferred through patterns, through the identities of particles before and after, through the careful matching of what must have occurred. This is how much of particle physics works. We do not watch the weak force with our eyes, we watch its consequences. The situation is a little like hearing a soft noise in another room and then finding the teacup moved, the biscuit gone, and the cat looking unusually innocent. You did not see the event itself, but the evidence is persuasive. In radioactive decay, the changed nucleus and emitted particles tell the story. The weak force leaves its signature in transformation. There is also a deeper meaning in the word decay. It can make the process sound like an ending, but in physics it is often more like a transition. The original nucleus changes into another nucleus. The emitted particles carry energy away. The universe moves from one allowed arrangement to another. Nothing has vanished into nothing. The pieces of the story have been redistributed according to the rules. Even when an unstable particle disappears, the underlying energy, momentum, charge, and other conserved quantities remain accounted for. Decay is not nature losing track. It is nature changing the entry in the ledger. This is especially clear in beta decay. When the neutron changes into a proton, The positive charge of the proton is balanced by the negative charge of the emitted electron. The antineutrino helps carry away energy and other necessary properties. The whole process obeys the rules. It may be strange, but it is not sloppy. In fact, the precision of these decays has made them powerful tools for testing the standard model of particle physics. By measuring weak decays very carefully, scientists can check whether the theory matches reality. Any tiny difference might hint at new physics beyond what we currently know. So radioactive decay is not just a natural hazard, a medical tool, or a dating method. It is also a window into the laws of matter. It reveals that the nucleus is not always permanent. It shows that protons and neutrons are related through deeper quark transformations. It confirms the existence and importance of neutrinos. It demonstrates the probabilistic nature of quantum events. And it gives the weak force one of its clearest roles, the power to change particles in ways that alter atoms themselves. This can make the ordinary world feel slightly less ordinary. The stable objects around us are stable because their particles and nuclei do not have easy allowed paths into other forms, or because any possible changes are so rare that they do not matter on everyday timescales. The world feels solid because most of its ingredients are steady, but hidden inside certain materials rare transformations continue. A nucleus changes, a particle leaves, a neutrino escapes, an element becomes another element. The table may look still, the stone may seem silent, but matter as a whole is full of histories happening at scales too small and too slow for unaided human senses. Radioactivity also helped change our understanding of energy. Before nuclear physics, energy was mostly understood through motion, heat, chemistry, and light. Radioactive materials show that atoms themselves contain deep reservoirs of energy. Later, the discovery of the nucleus and the study of nuclear reactions revealed just how much energy is bound inside atomic structure. The weak force was not the only part of that revolution, but weak decay was one of the pathways that opened the door. It showed that the atom was not indivisible, not inert, and not final. The atom had an inner life, and the inner life of the atom is not always gentle. Radiation can be harmful because energetic particles and rays can damage living tissue and break chemical bonds. That is why radioactive materials must be handled carefully. But radiation is also useful when understood and controlled. It can help diagnose disease, treat cancer, sterilize equipment, trace biological processes, and reveal the ages of ancient materials. Like many parts of nature, radioactivity is not simply good or bad. It is a process. Its effects depend on amount, context, shielding, distance, and use. The weak force itself is not dangerous in some personal sense. It is one of the rules by which certain particles change. The danger or usefulness comes from how those changes release radiation into the world of atoms and cells. This distinction matters because it keeps the science clear. The weak force is not a glowing substance. It is not a kind of poison. It is not radiation itself. It is an interaction, one of the fundamental ways particles affect and transform one another. In beta decay, the weak force permits the nuclear change. The emitted particles are the radiation we can detect. The force is the hidden rule. The radiation is the visible clue. So when we say the weak force is behind radioactive decay, we are really saying something precise. We are saying that certain unstable nuclei can become more stable by changing a neutron into a proton or a proton into a neutron. We are saying this transformation happens because the weak interaction can change quark type and produce leptons such as electrons, positrons, neutrinos, and antineutrinos. We are saying the process is probabilistic for individual atoms but predictable for large samples. And we are saying that from these tiny changes arise some of the most important tools and clues in all of science. There is a calm strangeness in that. A force too short range to feel, carried by particles too fleeting to imagine, can produce changes that help date ancient bones, warm the earth, reveal the sun's interior, and test the deepest theories of matter. It can turn one element into another. It can send neutrinos streaming through the universe. It can make the nucleus not just a center of mass and charge, but a place where identity changes. And those neutrinos, so easily missed and so closely tied to weak decay, now deserve our attention. Because whenever the weak force changes particles, neutrinos often appear like quiet messengers from the event, carrying away energy, preserving the balance, and passing through the world almost untouched. To understand the weak force more fully, we need to follow those ghostly messengers into the next part of the story. Neutrinos are among the strangest little messengers in the universe. They are everywhere, yet almost impossible to notice. They're born in some of the most energetic places nature can offer, deep inside stars, inside exploding stars, inside nuclear reactions, inside radioactive decay, and yet they pass through the world with such quiet indifference that you could have trillions of them moving through you and never feel a thing. In fact, that is not just possible, it is happening right now. As you listen, neutrinos from the sun are passing through your body, through the walls around you, through the floor, through the earth, and onward into space, as if the entire planet were no more substantial than a thin curtain. They do not ask permission. They do not stop for tea. They do not even slow down much. They simply pass through. This is why neutrinos are often called ghost particles. It is not because they are supernatural, of course. They do not haunt old houses or rearrange furniture in the night, though if they did, detecting them might be easier. They are called ghostly because they barely interact with ordinary matter. A neutrino can travel through enormous amounts of material without hitting anything. It can cross light years of space, pass through stars, planets, and living bodies, and continue almost unchanged. If most particles are guests at the cosmic dinner table, bumping into one another, exchanging energy, making light, forming atoms, and generally keeping busy, neutrinos are the quiet ones slipping through the room unnoticed. The reason for this ghostly behavior is closely tied to the weak force. Neutrinos do not feel the strong nuclear force. They have no electric charge, so they do not feel electromagnetism in the ordinary way. Gravity affects them, but because they are so incredibly light, gravity is not very useful for catching them. That leaves the weak force as their main way of interacting with other particles. And since the weak force acts only over extremely tiny distances, and is, as its name suggests, not very strong at ordinary energies, neutrinos are famously hard to catch. They are not invisible because they are hiding. They are invisible because they have very few reasons to care that matter is there. And yet, without neutrinos, the story of the weak force would feel unfinished. They appear again and again whenever particles change through weak interactions. In radioactive beta decay, when a neutron turns into a proton, an electron is emitted and an antineutrino slips away. In a related process where a proton becomes a neutron may be released. In the heart of the Sun, neutrinos are produced during the nuclear reactions that allow hydrogen to become helium. In supernova explosions, unimaginable numbers of neutrinos burst outward from the collapsing core, carrying away a huge amount of energy before light has even escaped. Neutrinos are the quiet receipts of transformation. They tell us that something deep has changed. Their story began as a solution to a problem. Early studies of beta decay revealed something troubling. The energy of the emitted electrons did not come out in one neat value. Instead, it spread across a range. That was strange because if the decay involved only the original nucleus, the new nucleus, and the emitted electron, then the energy should have been distributed more simply. It looked as if energy might not be conserved, and energy conservation is not the kind of rule physicists give up casually. It is more like the good teapot of physics. You do not throw it away unless there is absolutely no other option. So Wolfgang Pauli proposed a bold idea. Perhaps an unseen particle was being emitted along with the electron, carrying away the missing energy. This particle would have no electric charge, very little mass, and would be extremely hard to detect. It was, in a sense, invented to save the bookkeeping of nature. Later, Enrico Fermi developed a theory of beta decay that included this tiny neutral particle, and the name neutrino came into use. It means little neutral one, which is rather charming, like a nickname given to the shyest member of the particle family. For a while, the neutrino was only a hypothesis. It had to exist if the accounting was right, but it seemed almost impossible to observe. A particle that barely interacts is a difficult thing to prove. It is like trying to prove that a whisper passed through a room after everyone has already gone home. But eventually, neutrinos were detected through experiments near nuclear reactors, where enormous numbers of them were produced. Even with so many streaming through the detectors, only a tiny fraction interacted. The experiments required patience, cleverness, and a willingness to build equipment large enough to catch something that nearly always refuses to be caught. This is still true today. Neutrino detectors are often enormous. Some are buried deep underground, where layers of rock shield them from other particles that would create noise in the measurements. Some use vast tanks of water or other materials, waiting for the rare moment when a neutrino finally interacts with an atom inside. When that happens, the event may produce a tiny flash of light or a trace of a charged particle. That tiny signal becomes evidence that a neutrino passed through and, for once, did not get away completely. Imagine trying to detect rain by waiting for one drop in a storm to ring a bell at the bottom of a cave. That is roughly the level of patience involved, though with more electronics and fewer umbrellas. But why does the universe make so many neutrinos if they are so hard to notice? The answer is that weak interactions happen in many important places. Wherever certain particle transformations occur, neutrinos often appear. In beta decay, they carry away energy and other properties. In the Sun, they are produced during fusion processes. In supernovae, they are released in staggering numbers when a star's core collapses. Neutrinos may be difficult to detect, but they are not rare. They are some of the most abundant particles in the universe. The Sun is a particularly important source. Deep in its core, where temperatures and pressures are high enough for nuclear fusion, protons take part in a chain of reactions that eventually produces helium. One of the crucial early steps requires the weak force, because one proton must become a neutron. That transformation produces a neutrino. Unlike light, which can take a very long time to work its way out from the dense solar interior, neutrinos escape almost immediately. They stream straight out of the Sun and reach Earth in only minutes. In a way, solar neutrinos are direct messages from the Sun's core. The sunlight on your window has wandered through the Sun's interior in a slow and complicated journey before escaping. The neutrinos came almost straight from the source, like impatient little couriers who refused to wait in the lobby. This made neutrinos powerful tools for understanding the Sun. Scientists built detectors to count solar neutrinos and compare the results with predictions. At first, they found fewer neutrinos than expected. This became known as the solar neutrino problem. For decades it puzzled physicists. Was the theory of the Sun wrong? Were the detectors missing something? Or was something happening to the neutrinos on the way to Earth? The answer turned out to be one of the most important discoveries in modern particle physics. Neutrinos can change type as they travel. This process is called neutrino oscillation. Neutrinos come in three known types, connected to the electron, the muon, and the tau particle. A neutrino born as one type does not always remain that type. As it moves through space, it can shift between these identities. By the time it reaches a detector, it may no longer be the type the detector was originally designed to find. This explained why early solar neutrino experiments saw fewer neutrinos than expected. The missing neutrinos were not truly missing. Some had changed into types that the experiment did not easily detect. Once again, nature had not lost the receipt. It had filed it under another name. Neutrino oscillation also revealed something very important. Neutrinos have mass. Tiny mass, but mass nonetheless. This was surprising because the original simplest version of the Standard Model treated neutrinos as massless. The discovery that they change type and must have mass showed that the story was deeper. It opened a door to physics beyond the simplest picture. Even the ghostliest particles were carrying clues that our understanding was not complete. There is something almost poetic, though we should keep our feet on the scientific floor, about the fact that neutrinos change identity. The weak force already teaches us that some particles can transform. Neutrinos add another layer. They are born in weak processes, barely interact as they travel, and can change from one type to another along the way. They are not only messengers of change, they themselves are changing messengers. It is as if the universe sent a letter, and the envelope quietly changed colour while crossing the room. This ability to change type is not the same as beta decay. In beta decay, particles transform through a weak interaction at a specific event. Neutrino oscillation is a quantum process that happens as neutrinos travel, linked to the relationship between their type and their mass states. We do not need the technical machinery here, especially not while everyone is trying to stay peaceful, but the basic idea is that a neutrino's identity is not as simple as a single fixed label. It can be a mixture, and that mixture evolves over time and distance. By the time it arrives, the flavour may be different from the one it had when it began. This is another reminder that the particle world does not always match our everyday ideas of identity. A chair does not become a different kind of chair while crossing the room, unless someone in the house has unusually ambitious furniture. But neutrinos do something that, at ordinary scales, feels impossible. They shift between types because their quantum nature allows it. The result is measurable. It is not a metaphor, it is a real physical effect, confirmed by experiments using neutrinos from the sun, from the atmosphere, from reactors, and from particle accelerators. Atmospheric neutrinos give another example. Cosmic rays, which are high-energy particles from space, strike atoms in Earth's atmosphere and create showers of secondary particles. Some of those particles decay and produce neutrinos. These neutrinos then travel through the atmosphere, or even through the Earth, before reaching detectors. By comparing neutrinos arriving from different directions, scientists found evidence that they were changing type during their journey. Some travelled a short distance, others crossed the entire planet. The longer the journey, the greater the chance of oscillation. The Earth itself became part of the experiment, a planet-sized filter for ghost particles. Reactor neutrinos are also useful. Nuclear reactors produce large numbers of antineutrinos through beta decays in fission products. By placing detectors at different distances from reactors, scientists can study how antineutrinos change as they travel. Particle accelerators can produce controlled beams of neutrinos and send them through the ground to distant detectors. It sounds almost casual when said that way, but it is astonishing. Humans can create a beam of ghostly particles, send it through hundreds of kilometers of rock, and measure what arrives on the other side. The neutrinos do not need a tunnel. The planet is not much of an obstacle to them. They simply pass through, while the scientists wait with very large instruments and very patient expressions. Supernova neutrinos are perhaps the most dramatic. When a massive star collapses at the end of its life, the core becomes incredibly dense and hot. In that collapse, vast numbers of neutrinos are produced. They carry away most of the gravitational energy released in the event. Before the visible light of the explosion becomes obvious, neutrinos can escape from the core and race outward. In 1987, detectors on Earth observed a small burst of neutrinos from a supernova in a nearby galaxy. Only a few were detected, but those few were enough to confirm that our understanding of stellar collapse was on the right track. A dying star had sent out a flood of ghost particles, and a tiny handful left their marks in human instruments. That is one of the remarkable things about neutrinos. They let us see into places light cannot easily show us. Light interacts strongly with charged particles and can be scattered, absorbed, and delayed. Neutrinos barely interact, so they can escape from dense regions and carry information directly. They come from the sun's core, from nuclear reactors, from cosmic ray interactions, from exploding stars, and perhaps from some of the most extreme environments in the universe. They are difficult to catch, but when we do catch them, they tell us about hidden processes. This is why calling them messengers is more than a nice phrase. They genuinely carry information from weak interactions and nuclear events. In beta decay, a neutrino or antineutrino carries away part of the energy and helps preserve the rules. In the Sun, neutrinos tell us fusion is happening in the core. In supernovae, they reveal the deep collapse. In oscillation experiments, they tell us about their own masses and mixing. Each detected neutrino is a tiny report from a place or process that would otherwise remain partly hidden. Of course, neutrinos are not easy reporters to interview. Most of them pass through every detector without interacting. To observe them, scientists must rely on rare weak interactions. A neutrino may collide with a particle in the detector and produce a charged particle. That charged particle can then create a signal, often a small flash of light in the detector material. From the direction, energy, and type of signal, researchers infer the neutrino's properties. It is indirect work, but that is often how deep physics is done. The universe does not always hand us simple photographs. Sometimes it leaves a faint footprint and asks us to reconstruct the visitor. Neutrinos also connect to the question of antimatter. For each neutrino type, there is an antineutrino. In many weak processes, neutrinos and antineutrinos appear in ways that preserve deeper particle rules. But one of the great open questions is whether neutrinos and antineutrinos might be related in a special way, perhaps even being two versions of the same underlying particle. If that were true, it could have major implications for why the universe contains more matter than antimatter. This remains an active area of research. It is one of those places where the smallest and quietest particles may hold clues to the largest mystery of cosmic history. Neutrinos may also be connected to the unseen mass of the universe. Though ordinary known neutrinos cannot explain most dark matter, they are too light and move too quickly to form the kind of structure we observe. Still, their mass matters for cosmology. Because there are so many neutrinos in the universe, even tiny masses can influence how structures formed over cosmic time. The ghost particles are not heavy enough to be the whole hidden scaffolding of the cosmos, but they are not irrelevant either. They are part of the inventory, part of the background, part of the quiet traffic moving through everything. It is fascinating that particles so difficult to detect are so important. We often associate importance with visibility. The bright star, the large planet, the heavy stone, the loud thunder. Neutrinos are the opposite. They are almost not there from the point of view of ordinary matter, and yet they are essential to understanding weak interactions. They reveal how particles change, how stars burn, how supernova collapse, how the standard model needs extension, and how the universe keeps its hidden accounts. They also give the weak force a kind of signature. Whenever neutrinos appear, the weak force is usually nearby in the story. That does not mean every weak interaction must be explained only through neutrinos, but neutrinos are deeply tied to weak processes. They are produced by weak decay. They are detected through weak interaction. They change type in ways that reveal physics beyond the simplest model. They are the soft footsteps of the weak force across the universe. So if the weak force is the hidden door through which particles can change identity, neutrinos are often the quiet messengers that slip through with news of what happened. A neutron changed into a proton, and an antineutrino left the room. A proton changed into a neutron, and a neutrino carried away the balance. A star fused hydrogen in its core, a neutrino streamed outward. A supernova collapsed, and neutrinos rushed ahead of the light. They do not shout, they do not shine, they barely touch anything, but they carry the evidence. There is a gentle wonder in imagining them passing through you right now, not in a way that should alarm you. They pass through because they interact so rarely. They have been doing this since before humans existed, before Earth had cities, before there were eyes to look up at the sun. Solar neutrinos have crossed every ocean, every forest, every sleeping creature, every quiet room. They are part of the constant invisible weather of the universe, a rain that does not wet, a breeze that does not move the curtains, and as we follow them back to their source, we find the weak force again and again. It is there in the decay that produces them. It is there in the rare interactions that let us detect them. It is there in the solar reactions that send them outward. The neutrino is difficult to catch because the weak force is so limited in reach. But that same difficulty makes it precious. A particle that barely interacts can travel from places no ordinary signal can escape. Its weakness becomes its gift. Still, to understand how the weak force actually makes these transformations happen, we need to meet the carriers of the force itself. Every fundamental interaction has its messengers, its exchange particles, its way of communicating change between the ingredients of matter. For electromagnetism, the photon plays that role. For the weak force, the messengers are far heavier, far shorter lived, and much more hidden. They are called the W and Z bosons, and they are the next strange figures waiting in the quiet machinery of particle change. If neutrinos are the quiet messengers that slip away from weak interactions, then the W and Z bosons are the hidden carriers that make those interactions possible in the first place. They are not familiar particles in the way electrons or photons are familiar. They do not build the ordinary matter you touch. They do not make up tables, air, water, or the soft edge of a blanket. They do not travel across the room as light does. They are heavy, short-lived, and so deeply tied to tiny distances that their presence in everyday life is almost completely indirect. And yet, without them, the weak force would have no way to do its strange work of changing particles. The idea of a force carrier may feel a little odd at first. In daily life, a force often seems like something direct. You push a door and the door opens. You pull a drawer and the drawer slides. Gravity pulls you toward the ground without needing to send a tiny delivery note first, at least not in any way our senses can detect. But in modern particle physics, forces are described through fields and exchange particles. The interaction between particles is linked to the exchange of force-carrying particles, sometimes called bosons. These bosons are not little messengers in the ordinary sense, wearing caps and running between particles with tiny envelopes. But that image is not entirely useless if we handle it gently. They are the way an interaction is communicated in the quantum world. For electromagnetism, the force carrier is the photon. A photon can be thought of as the particle of light, but it also carries electromagnetic interactions between charged particles. Photons have no mass, and because of that, electromagnetism can reach across long distances. Light from a star can travel for billions of years. Radio waves can cross cities. Electric and magnetic fields can extend far beyond the tiny particles that create them. Electromagnetism is long-ranged, visible, practical, and constantly involved in ordinary life. It is there in your eyes receiving light, in the chemistry of your body, in the signals moving through your nerves, and in the screen or speaker bringing these words to you. The weak force is different because its carriers are not massless. They are very heavy, much heavier than protons or neutrons. The W and Z bosons are some of the heaviest particles in the Standard Model. They are so heavy that creating them requires high energy, and when they appear, they vanish very quickly. This heaviness is the reason the weak force acts only over a tiny range. It cannot reach across an atom, let alone a room. Its influence is confined to distances far smaller than the size of a proton. If electromagnetism is like a voice that can echo across a valley, the weak force is like a whisper so short that it barely leaves the speaker's lips. That tiny range explains why the weak force does not feel like a force in ordinary experience. You do not feel it tugging at your hand. You do not see it glowing in the air. You cannot hold two objects near one another and watch the weak force pull them together. It is there, but it acts inside the small quantum events where particles transform. The W and Z bosons are the hidden agents of those events. They appear briefly as part of the weak interaction, allowing particles to exchange charge, change flavor, or scatter in ways that only the weak force permits. there are 3 weak force carriers. 2 of them are the charged W bosons, one carrying positive charge and one carrying negative charge. The third is the neutral Z boson. Their names sound plain, almost like labels on storage boxes in a very serious laboratory. But their roles are anything but plain. The charged W bosons are especially important in the kinds of transformations we have already been discussing. They can mediate processes where a quark changes from one type to another, or where a lepton changes within a weak interaction. When a neutron decays into a proton, one of the quarks inside it changes identity, and that change is associated with a W boson. The W boson then produces an electron and an anti-neutrino. It is not a long journey. It is not a little ball flying across a visible space. It is a brief quantum event, a tiny handoff in the language of fields. The Z boson works differently. It is neutral, so it does not change electric charge in the same way. It is involved in weak interactions where particles scatter without changing charge. These are called neutral current interactions. A neutrino, for example, can interact through the exchange of a Z boson and remain a neutrino afterward, though its energy and direction may change. This is one of the ways neutrinos can be detected, though such events are rare. The Z boson allows the weak force to act without the dramatic identity change associated with the charged W bosons. If the W boson is the one that helps particles switch roles, the Z boson is more like the one that allows a quiet nod across the room, though the room in this case is smaller than an atomic nucleus, and the nod is a quantum interaction. One of the surprising things about the W and Z bosons is that they were predicted before they were directly discovered. Physicists did not simply stumble across them one afternoon like lost coins under a sofa. They emerged from the theoretical structure that unified the weak force with electromagnetism. In the 20th century, scientists realized that the weak force and electromagnetism were deeply connected. At ordinary energies, they look extremely different. Electromagnetism is long-ranged and carried by massless photons. The weak force is short-ranged and carried by massive W and Z bosons. But at very high energies, the two forces become aspects of a single electro-weak interaction. This was one of the great achievements of modern physics. The electroweak theory required the existence of the W and Z bosons. Their masses and roles were not arbitrary decorations added later. They were part of the theory structure. But predicting particles is one thing, finding them is another. Because the W and Z bosons are so heavy, they cannot be produced easily in ordinary conditions. Particle accelerators were needed to concentrate enough energy into tiny regions, allowing these heavy bosons to appear briefly before decaying into lighter particles. In the early 1980s, experiments at CERN detected them. It was a major confirmation of the electroweak theory, and a powerful sign that the standard model was describing something real about the deep workings of nature. There is a nice human lesson in that story. Sometimes physics finds invisible things by following the shape of the rules. The W and Z bosons were not guessed randomly. They were required because the theory needed carriers for the weak interaction that fit with the larger electroweak framework. When experiments finally found them, it was like hearing a note that had been written in the score long before the instrument was built to play it. The theory had pointed into the darkness, and the detectors answered. But why are they so heavy? This question leads us toward one of the most famous ideas in modern physics, the Higgs field. The W and Z bosons gain mass through their interaction with the Higgs field. The photon, by contrast, remains massless. This difference helps explain why electromagnetism reaches far while the weak force remains short-ranged. The details can become technical very quickly, and we do not need to wander too far into that machinery tonight. But the basic idea is that the universe is filled with a field that gives mass to certain particles through their interaction with it. The W and Z bosons interact strongly with this field, becoming heavy. The photon does not acquire mass in the same way, and so light remains able to roam freely across cosmic distances. The discovery of the Higgs boson in 2012 helped complete this part of the Standard Model. It confirmed the existence of the field associated with a mechanism that gives mass to the W and Z bosons, among other particles. That discovery did not make the weak force less mysterious, but it made the picture more coherent. The weak force is short-ranged because its carriers are massive. Its carriers are massive because of the way electroweak symmetry is broken by the Higgs field. The universe, as usual, has a perfectly sensible explanation that sounds deeply strange when said out loud. The heaviness of the W and Z bosons also explains why weak interactions are relatively rare at low energies. To produce or exchange such heavy carriers, particles must operate under quantum rules that allow brief intermediate states, but those states are difficult and limited. The interaction can happen, but it is suppressed. That suppression is why neutrons decay over minutes rather than instantly. It is why neutrinos can cross enormous distances without interacting. It is why the weak force, despite its importance, remains hidden behind the scenes. The carriers are powerful in role but costly in energy. Nature can use them, but not casually. This helps explain a curious point. The weak force is not weak because its carriers are unimportant. It is weak at ordinary energies because its heavy carriers make the interaction short-ranged and less likely. If you could get close enough and energetic enough, the weak force would not seem so feeble. In the hot early universe, when energies were far higher, the weak force and electromagnetic force behaved as one electroweak interaction. The weakness we see now is partly a feature of our cool low-energy universe. We live long after that early fire cooled, in a world where the forces have settled into separate personalities. There is something almost domestic about that idea. The early universe was too hot and energetic for the forces to look as they do now. As it cooled, the rules took on their familiar shapes. Electromagnetism remained long-ranged and bright. The weak force became short-ranged and hidden. The W and Z bosons became heavy. Particles gained masses. Matter took forms that could eventually build atoms. The quiet world we know is the cooled result of an earlier, stranger unity. The weak force carries a trace of that ancient condition, like a family resemblance from the universe's earliest childhood. Now, when we speak of a W boson in a decay, it is important not to imagine it as a stable particle sitting around inside a neutron waiting for its turn. A neutron does not contain a little W boson tucked away like emergency equipment. In beta decay, the W boson appears as part of the interaction. It is often described as virtual, meaning it is an intermediate feature of the quantum process rather than a directly observed free particle in that situation. It exists briefly within the rules of the interaction, and then gives rise to the particles that emerge. This language can be confusing because virtual does not mean imaginary in the casual sense. It means the particle is not observed as a normal free particle on its own, but it still plays a real role in the calculation and the interaction. In high-energy particle accelerators, W and Z bosons can be produced as real particles, though they decay almost immediately. Physicists detect them by looking at the particles they decay into. A W boson might decay into a charged lepton and a neutrino, or into combinations involving quarks. A Z boson can decay into pairs of particles and antiparticles, such as an electron and its antimatter partner, or a pair involving other leptons or quarks. The boson itself is too short-lived to watch directly in a simple way. Instead, researchers reconstruct its presence from the debris, like identifying a vanished firework from the pattern of sparks left in the sky. This reconstruction is one of the great arts of particle physics. Detectors record tracks, energies, flashes, and missing momentum. Neutrinos escape without leaving direct tracks, so their presence must often be inferred from what seems to be missing. The W and Z bosons are identified through statistical patterns across many collisions. One event may be interesting. Many events together reveal the particle. It is a reminder that the subatomic world often speaks in crowds, not in single clear sentences. The W boson is especially tied to change in electric charge. In weak charge current interactions, particles can exchange charge through the W boson. This is what allows a down quark to become an up quark, or an up quark to become a down quark in the right circumstances. Because protons and neutrons differ by the quarks inside them, this quark change can turn one into the other. In beta decay, the W boson is the connection between the changing quark and the emitted lepton particles. It is the carrier of transformation. That is why the W boson is so central to the weak force's identity-changing power. The Z boson, being neutral, does not carry electric charge from one particle to another, but it still allows weak interaction. It is involved in processes that reveal the weak force without changing the particle's electric charge. Neutrinos scattering through the Z boson was an important confirmation of electroweak theory. It showed that the weak force had both charged and neutral currents, just as the theory predicted. The Z boson may not feel as dramatic as the W boson in the story of particle transformation, but it is just as essential to the full structure. A quiet role is still a role. Physics, like a good orchestra, needs more than the trumpet. The discovery and study of these bosons also helped show how precise the Standard Model can be. Their masses, decay patterns, and interactions can be measured and compared with theoretical predictions. Small differences matter. Scientists continue to measure the W boson's mass with great care, because any mismatch between prediction and observation could point toward new physics. The Standard Model is remarkably successful, but it is not the final word. It does not explain dark matter. It does not fully explain neutrino masses. It does not include gravity in a quantum way. So every precise measurement becomes a searchlight aimed at the edge of what we know. This is another reason the W and Z bosons are so important. They are not just carriers of an obscure force, they are testing grounds for the structure of the universe. They connect the weak force to electromagnetism. They connect particle masses to the Higgs field. They connect nuclear decay to high-energy experiments. They connect the quiet transformation of a neutron to the grand architecture of the Standard Model. That is a remarkable career for particles that live for such an unbelievably short time. It can be helpful to imagine the weak force as a narrow bridge between particle identities. The W bosons are part of the bridge mechanism that allows charge transformations. The Z boson allows neutral weak interactions. The bridge is extremely short, almost hidden inside the foundations of matter. Most particles never cross it under ordinary conditions, but when they do, the result can be profound. A neutron becomes a proton. A neutrino scatters. A particle decays. A star begins one of the steps that leads to light. The bridge is tiny, but the paths it permits reach into the story of everything. There is also a strange elegance in the fact that the weak force can both change particles and reveal deep asymmetries in nature. The W and Z bosons do not interact with all particle states in the same simple way. The weak force has a preference for certain-handedness, a feature that will matter later when we talk about symmetry. This means the W and Z bosons are not just heavy carriers. They are carriers of a force that treats the mirror world differently. The weak interaction has opinions, so to speak, about left and right. That discovery shook physicists because it showed that nature is not always mirror-balanced at the deepest level. For now, the key point is that the weak force needs messengers, and those messengers are heavy. Their heaviness makes the force tiny in range. Their charged and neutral forms explain different kinds of weak processes. The W bosons allow transformations where charge and particle flavor change. The Z boson allows neutral weak interactions. Together, they turn the weak force from an abstract idea into a working mechanism, one that can be tested, measured, and connected to the rest of particle physics. And that mechanism is not hidden only in laboratories. It is also hidden in the sun, deep in the solar core where pressure and temperature are high enough for nuclear fusion. The weak force performs one of its most important acts. It helps turn one proton into a neutron, allowing the chain of reactions that powers sunlight to begin. Without that tiny weak step, the sun would not shine in the steady way we know. The W boson, brief and heavy and invisible to ordinary life, is part of the reason morning light can enter a room so gently. So from these heavy carriers of a tiny force, we can now follow the story outward again, from the subatomic event to the star that lights our days. The sun looks simple from far away. It rises, it brightens the sky, it warms the ground, and it sets behind rooftops, trees, hills, oceans, or whatever happens to be blocking your particular horizon. To most of us, it is just there, a bright familiar disk that marks the day, and occasionally makes us regret forgetting sunglasses. But inside that ordinary-looking star is one of the most important hidden processes in the universe. Deep in its core, matter is being changed. Hydrogen is being turned into helium. Energy is being released. Light is beginning a long journey outward. And quietly, almost secretly, the weak force is helping make it possible. This may sound strange at first because when people think of the sun, they usually think of heat, light, fire, and perhaps a very strong reminder to wear sunscreen. The weak force does not sound like the sort of thing that should be involved. It sounds too small, too shy, too hidden. Yet the sun depends on it. Not because the weak force provides most of the energy directly, and not because it throws light across space like a lantern. The weak force matters because it allows a crucial transformation at the start of the sun's main fusion process. It lets one kind of particle become another at exactly the point where the solar story needs it. The sun shines because of nuclear fusion. In its core, the pressure and temperature are enormous. Gravity has squeezed the sun's gas inward with such persistence that the central region becomes incredibly dense and hot. At those conditions, atomic nuclei move very quickly, colliding again and again. Most of the sun is hydrogen, and the nucleus of a hydrogen atom is simply a proton. So deep in the sun, there is a vast sea of protons rushing, pressing, colliding, and trying to get close enough for nuclear reactions to happen. But protons have a problem. They all carry positive electric charge, and like charges repel. That means two protons do not naturally want to sit close together. They push each other away through electromagnetism. To fuse, they must come extremely close enough for the strong nuclear force to take over and bind particles together. The strong force is powerful at very short distances, but it cannot help until the protons are already nearly touching. So the sun's core is a place where protons are constantly trying, mostly failing, and occasionally succeeding in getting close enough for fusion to begin. It is less like a smooth factory line, and more like an unimaginably crowded dance floor, where almost every attempted handshake is rejected by electric repulsion. Even when two protons do come close enough, another issue appears. A stable helium nucleus cannot be built from protons alone. Helium needs both protons and neutrons. So if the sun is going to turn hydrogen into helium, some protons must become neutrons along the way. That is where the weak force enters. In the first major step of the sun's main fusion chain, two protons come together, and one of them changes into a neutron. The result is a small nucleus made of one proton and one neutron, along with a positron and a neutrino. That small nucleus is called deuterium, a heavier form of hydrogen, and once deuterium exists, the rest of the chain can continue more easily. This first step is the difficult one. It is slow, it is rare. It depends on the weak force because changing a proton into a neutron requires a change in the identity of one of its quarks. A proton and a neutron are not wildly different objects. They are close relatives, both made of quarks, both living in the family of particles that build atomic nuclei. But they are not the same. To turn one into the other, a quark must change type, and the weak force is the interaction that allows that. Without the weak force, the sun's main path for fusion would be blocked at the start, like a long road with the first gate locked. This is the hidden importance of weakness. The weak force is slow in this process, and that slowness is not a defect. It is part of why the sun lives so long. If protons could transform into neutrons easily, the sun might burn through its fuel much faster. Its brightness, lifetime, and stability would be very different. The fact that this first step happens only rarely means the sun releases energy at a steady pace over billions of years. It is not exploding through its fuel in a brief cosmic flare. It is shining with patience. The weak force, by being difficult and selective, helps turn the sun into a long-lasting star rather than a short-lived disaster with excellent lighting. This is one of those cases where a process being inefficient is exactly what makes it useful. In everyday life, inefficiency can be annoying. A slow kettle, a delayed bus, a printer that appears to be thinking about its childhood instead of printing. But in the sun, the slowness of the weak step is a gift. It sets the pace. It allows the core to produce energy steadily. It helps give Earth a stable source of light and warmth over geological time. Life on this planet depends not merely on the sun being powerful, but on the sun being controlled. Too much too quickly would be catastrophic. Too little would leave the planets cold. The weak force helps keep the solar furnace from burning too fast. Once deuterium forms, it can fuse with another proton, producing a light form of helium. Then, through further steps, helium nuclei are eventually produced. Across the whole chain, a small amount of mass is converted into energy. That energy first appears deep inside the solar core, not as the gentle sunlight you see through a window, but as high-energy radiation and motion among particles in the dense plasma. From there, the energy begins an extremely long and complicated journey outward. Light created in the sun's interior does not simply fly straight to the surface. The core is dense. Photons are absorbed and re-emitted again and again, scattered in countless directions. Their path outward is more like a slow, random walk than a straight line. A photon born deep inside the sun may take a very long time to escape, being passed around through the solar interior like a message in a crowd where everyone keeps changing their mind about which way the exit is. Eventually, after much wandering, the energy reaches the surface and is released into space as sunlight. That sunlight then travels to Earth in just over 8 minutes, crossing the distance from the sun to your face, your wall, your garden, or your sleepy little room. The neutrino produced in the weak step behaves very differently. It does not wander through the sun for ages. Because neutrinos interact so rarely, the solar material hardly slows them. They stream almost directly out from the core and into space. They reach Earth in minutes, carrying fresh information from the place where fusion is happening right now. This makes solar neutrinos extremely valuable. They are direct messengers from the sun's core. Light tells us about the sun's surface as it is now, and about energy that may have begun deep inside long ago. Neutrinos tell us about the nuclear reactions happening deep within the sun in the present. This was one of the great reasons scientists wanted to detect solar neutrinos. If the theory of solar fusion was correct, then the sun should be producing neutrinos in predictable numbers. Detecting them would confirm that the weak processes inside the core were truly happening. But as we heard before, neutrinos are very hard to catch. They pass through matter so easily that even an enormous detector sees only a tiny fraction of them. Early experiments did detect solar neutrinos, but fewer than expected. For a long time, this was a serious puzzle. Either our model of the sun was wrong, or something unexpected was happening to the neutrinos during their journey. The solution was neutrino oscillation. Neutrinos born in the sun as one type can change into other types while traveling through space. Early detectors were mostly sensitive to only one type, so they missed the others. The sun was not producing too few neutrinos. The neutrinos were changing identity on the way. This discovery was a triumph for both solar physics and particle physics. It confirmed the sun's fusion processes while revealing that neutrinos have mass and can change type. Once again, the weak force and its ghostly messengers had opened a door into deeper reality. There is something wonderfully layered about this. The sun uses the weak force to begin a fusion step. That step produces neutrinos. The neutrinos travel to Earth. Their changing types reveal new physics. and the detection of those neutrinos confirms what is happening in the solar core. The weak force is not just helping the sun shine, it is also helping us understand how the sun shines. It provides both the mechanism and the message. To appreciate this more fully, imagine the sun without the weak force. Gravity would still pull matter inward, protons would still exist, electromagnetic repulsion would still make it difficult for them to come together. The strong force would still bind particles at very short distances. But the crucial transformation of a proton into a neutron would not occur through the same pathway. The main chain that powers stars like the sun would be profoundly altered. The sun might not shine steadily as it does. It might not support the long calm timescales that allowed Earth to cool, oceans to form, continents to shift, life to evolve, and eventually someone to lie down and listen to a quiet explanation of particle physics. That is a lot to owe to a force with such a modest name. The weak force also helps determine which stars shine in which ways. In stars like the sun, the proton chain is the dominant fusion route. In more massive stars, another fusion cycle involving carbon, nitrogen, and oxygen becomes more important, though the weak force still plays important roles in the transformations that occur. Across stellar physics, weak interactions help regulate processes involving neutrinos, neutron production, and changes in nuclear composition. Stars are not just burning balls of gas, they are nuclear systems governed by the four fundamental forces, each doing its own particular work. Gravity gathers the star. Electromagnetism resists, radiates, and shapes plasma behavior. The strong force binds nuclei and releases energy through fusion. The weak force permits the particle transformations that allow certain chains to proceed. The balance between these forces is delicate. Gravity tries to compress the sun. Pressure from hot plasma and radiation pushes outward. Fusion in the core supplies the energy that maintains this balance. If fusion slowed too much, gravity would press the core inward, heating it and changing the reaction rates. If fusion rose too much, outward pressure would expand the core and cool it. In this way, the sun regulates itself over long periods. It is not a frozen object. It is a dynamic balance, a star held in steady tension between inward pull and outward pressure. The weak force participates in that balance by controlling one of the key bottlenecks in energy production. A bottleneck may sound like a problem, but in the sun it is essential. The slow, weak step prevents fusion from racing ahead uncontrollably. Most proton collisions in the solar core do not result in the weak transformation needed to create deuterium. They simply scatter apart. Only rarely does the right quantum event happen, yet the sun contains so many protons and so many collisions that even a rare process produces enormous energy overall. This is another strange lesson from physics. A rare event, multiplied by the vastness of a star, becomes a steady blaze. The weak force acts seldom in each individual encounter, but the sun is so enormous that seldom is still enough to light the solar system, and the energy released is not just brightness, it is the foundation of Earth's surface environment. Sunlight drives weather, warms oceans, powers photosynthesis, and sets the rhythms of climate and life. Plants capture sunlight and build sugars. Animals eat plants or eat other animals that ate plants. Winds move because the sun heats Earth unevenly. Rain falls because sunlight helps evaporate water. Even fossil fuels store ancient sunlight captured by life long ago. The weak force is not directly stirring clouds or growing leaves, but it stands near the beginning of the chain. It helps make the sun a steady source of energy, and that energy spreads into almost every living process we know. This does not mean the weak force alone is responsible for life, of course. Nature rarely gives one actor the whole script, but it does mean that the weak force is part of the hidden foundation. Remove it or change it significantly, and the story of stars changes. Change stars, and the story of planets changes. Change planets, and the story of life changes. A tiny force acting in the core of a star becomes part of the reason forests grow and mornings exist. There is also a connection to time. The sun has been shining for billions of years and will continue for billions more. Its long life is made possible because fusion proceeds at the pace set by the conditions in the core and by the weakness of that first transformation. The weak force helps make the sun not just bright, but enduring. It gives the solar system a long stable era. That long stability matters enormously. Life did not appear and become complex in a moment. It needed deep time. It needed oceans that persisted, climates that shifted but did not vanish overnight, and energy that kept arriving day after day. In that sense, the weak force helps give life the time it needs. This is a very different picture from the simple idea of the sun as a ball of fire. Fire is chemistry. It consumes fuel by rearranging electrons in molecules. The sun is nuclear. It changes atomic nuclei. It does not burn in the way wood burns. There is no oxygen feeding flames in the solar core. Instead, nuclei fuse under pressure and heat, and the weak force allows key particle changes that chemistry could never perform. Calling the sun a fireball is understandable, but it misses the deeper truth. The sun is a gravity-held nuclear furnace, and one of its most important switches is operated by the weak interaction. The word operated is only a metaphor, of course. There is no hand, no switch, no little worker inside the sun choosing when a proton should become a neutron. The weak force is a rule of interaction, a possibility built into the structure of particles and fields. Under the right conditions, with the right quantum chance, the transformation can happen. The sun does not decide. It simply contains the conditions where these rare weak events occur often enough across its immense core to keep the light coming. That is perhaps the most peaceful part of the story. The sun does not try to shine. It shines because the laws of nature make shining possible. Gravity gathers matter. Heat and pressure rise, particles collide. The strong force binds, the weak force transforms. Energy escapes. Light crosses space. A morning arrives. None of this needs intention. It is the quiet outcome of rules working together across scales, from quarks inside protons to sunlight across a planet. When sunlight enters your room, it has already passed through many stages. It began with conditions in the solar core where protons collided and rare weak transformations helped build the first steps of fusion. Energy moved through dense solar layers, scattered and reshaped until it reached the surface. Then light travelled across space to Earth, through the atmosphere, perhaps through glass, and finally into your eyes or onto the wall near your bed. The warmth feels simple, the path behind it is not, and somewhere in that path neutrinos streamed ahead, almost unnoticed. They left the core directly and passed through Earth whether it was day or night. Even when the sun is below your horizon, solar neutrinos are still passing through you from beneath your feet, having crossed the entire planet with barely a pause. It is a funny thought. At midnight, when the sky's dark and the sun seems gone, its neutrinos are still arriving. The weak force has sent a message through the Earth itself, and the Earth, mostly, has let it pass. That invisible flow is a reminder that the sun is not just something we see, it is something we detect in many ways. Light shows us the surface, neutrinos show us the core, gravity holds us in orbit, solar wind touches Earth's magnetic field. The sun is a whole system of signals, and the weak force is responsible for some of the most secretive ones. The star speaks in light, heat, particles, and ghostly whispers. Neutrinos are the whispers. The weak force also appears in later stages of stellar life. In massive stars, as nuclear burning progresses and cores become denser, weak interactions can change protons into neutrons and produce neutrinos that carry energy away. In the collapse of a massive star, weak processes become central to the formation of neutron-rich matter and the flood of neutrinos released in a supernova. The same force that quietly helps the sun shine also plays a role in the violent deaths of larger stars. It is gentle in one setting, catastrophic in another, not because the force changes its nature, but because the environment changes around it. This is a useful reminder that physics is contextual. A rule can produce different outcomes under different conditions. In the Sun, the weak force helps regulate steady fusion. In radioactive decay, it changes unstable nuclei over time. In supernovae, it helps drive transformations in collapsing stellar cores. The same interaction appears in quiet sunlight, laboratory detectors, nuclear dating, and cosmic explosions. Small does not mean simple. Weak does not mean minor. So when we ask how the Sun uses the weak force to shine, the answer begins with a tiny act of transformation. A proton becomes a neutron, a neutrino is released, a path opens for deuterium to form. From there, fusion continues, energy is released, and the long journey towards sunlight begins. The weak force does not make the Sun shine alone. It is not the whole furnace. But it is one of the keys that lets the furnace work in the steady way we know. And in that steady working, the weak force connects the smallest scale to the largest experience. A quark changes identity inside a proton. A nuclear reaction proceeds. A star releases energy. A planet receives warmth. Life wakes, grows, rests, and listens. The weak force is hidden at the beginning of that chain, almost impossibly small, yet its consequences spill across space as daylight. Still, the weak force has one more strange habit that makes it unlike the other forces in a particularly surprising way. It does not treat all directions and mirror images equally. It seems to care about handedness. It has a preference built into its deepest behaviour, as if nature itself were not quite as symmetrical as a mirror would like us to believe. To understand that, we need to turn from the Sun's glowing core to one of the most unexpected discoveries in particle physics, the strange left-handed bias of the weak force. One of the first things we tend to expect from nature is fairness. Not moral fairness, of course. The universe does not appear to worry about who got the larger slice of cake, but physical fairness, balance, symmetry. The idea that if you flip something around, turn it over, or look at it in a mirror, the basic laws should still make sense. A ball does not suddenly forget how to fall because you view it from the left instead of the right. A planet does not change its orbit because someone draws the diagram from the other side. Most of the time, nature seems quite comfortable with symmetry. It repeats patterns, balances charges, and often treats opposite directions as equally valid. That is why the weak force came as such a shock. For a long time, physicists assumed that the laws of nature were mirror-symmetric. This idea is often called parity symmetry. In simple terms, parity asks whether a physical process would still be allowed if everything were reflected in a mirror. Imagine watching a film of some experiment. Now imagine watching the mirror image of that same film. Would the mirror version still look like something that could happen in the real universe? For gravity, electromagnetism, and the strong force, the answer appears to be yes. Their basic behaviour does not seem to care whether the process is viewed normally or reflected. Left and right are treated as equals. The weak force does not do this. The weak force has a preference. It treats left-handed and right-handed particles differently. That sentence may sound strange because particles do not have hands, and if they did, they would be far too small to knit gloves. But in particle physics, handedness is a way of describing how a particle's spin relates to its direction of motion, and more deeply, how the particle behaves under the rules of relativistic quantum theory. We can use a simpler picture to begin. Imagine a tiny particle moving forward while also having a kind of internal twist. If the twist and the motion line up in one way, we call it right-handed. If they line up the other way, we call it left-handed. It is a little like the difference between a screw that turns clockwise as it moves forward and one that turns the opposite way. This picture is not perfect, but it helps. The important point is that particles can have a kind of handedness, and the weak force cares about it. In fact, the charged-weak interaction acts only on left-handed particles and right-handed antiparticles. That is one of the strangest and most important facts in the Standard Model. Nature, at this deep level, is not perfectly ambidextrous. The weak force does not shake both hands equally. It strongly prefers one. This was not expected. Physicists in the early 20th century were used to the idea that the mirror image of an allowed process should also be allowed. It felt sensible. It felt elegant. It felt like the kind of rule nature would choose if nature had been asked to keep the furniture neatly arranged. But experiments forced a different conclusion. In the 1950s, some physicists began to question whether parity symmetry had actually been tested in weak interactions. It had been assumed, but not proven. That is an important distinction in science. Sometimes an idea feels so natural that everyone treats it as true, until someone asks whether the universe ever signed the agreement. The decisive experiment was performed by Chien-Shiung Wu and her collaborators. They studied the radioactive decay of cobalt atoms at extremely low temperatures, with the nuclei aligned in a magnetic field. The goal was to see whether the emitted electrons preferred one direction relative to the nuclear spin. If nature respected mirror symmetry in this weak decay, the electrons should have been emitted in a mirror-balanced way. But they were not. The electrons came out more often in one direction than the mirror-symmetric expectation allowed. The weak force had violated parity. The mirror version of the process was not treated as equally valid. This result was stunning. It showed that the weak interaction could tell left from right. It meant that if you watch certain weak processes in a mirror, the reflected version would not match how nature actually behaves. The universe, at least through the weak force, had a handedness built into it. A mirror could show a world that looked ordinary to the eye, but at the level of weak decay, the mirror world would not follow the same rules. That is a very deep kind of asymmetry. We're used to left and right being relative. Your left is someone else's right if they stand facing you. A glove fits one hand but not the other, yet both hands seem equally natural. A spiral shell may twist one way or another, but physics itself does not usually appear to favour one direction. The weak force changed that expectation. It revealed that, at the smallest scales, nature has a preference that cannot be removed simply by turning the room around. This discovery also had a strong emotional effect on physics. Not sentimental emotion, but the kind of intellectual jolt that comes when a trusted principle fails. Symmetry had become a guiding idea in modern physics. It still is. Symmetries help physicists build theories, predict particles, understand conservation laws, and organize the behavior of forces. When parity violation was discovered, it did not destroy the importance of symmetry. Instead, it made symmetry more interesting. It showed that not every symmetry is respected by every force. Some symmetries are exact. Some are approximate, some are broken, and broken symmetries can be just as revealing as perfect ones. The weak force is especially revealing because it does not merely break mirror symmetry a little in some obscure corner. Its left-handed preference is built directly into how it interacts with fermions, the matter particles such as quarks and leptons. The W bosons, which carry charged weak interactions, couple to left-handed particles and right-handed antiparticles. This is why neutrinos became so central to the story. For a long time, neutrinos were observed only in left-handed forms, while antineutrinos appeared right-handed. This fit perfectly with the weak force's strange preference. Neutrinos make the idea feel especially sharp because they are so hard to detect in every other way. They barely interact at all, but when they do, they reveal the handedness of the weak interaction. A neutrino is not just ghostly because it slips through matter. It is also linked to one of nature's deepest asymmetries. It belongs to a force that seems to look at left and right and quietly choose. Now, there is a subtlety here. In modern physics, handedness can mean more than one related thing. There is a property called helicity, which has to do with the direction of a particle's spin compared with its motion. There is also chirality, which is more fundamental in the mathematics of the weak interaction. For massless particles, these ideas line up neatly. For particles with mass, they are not exactly the same. Neutrinos were once thought to be massless, which made the story seem simpler. Now we know neutrinos have tiny masses, which makes the details richer and more complicated. But for our calm journey, the main idea remains clear. The weak force distinguishes between particle-handedness in a way the other familiar forces do not. This is not just a strange footnote. It affects how particles interact and decay. When a neutron decays, the weak force is involved in changing one of its quarks and producing an electron and an antineutrino. The directions and spins of those emitted particles are not random in a fully mirror-balanced way. They carry the signature of the weak force's handedness. In particle accelerators, weak interactions also show this preference. The patterns of decay, scattering, and neutrino behavior all reveal that the weak force has a built-in asymmetry. The mirror violation of the weak force raises a simple question that is very hard to answer. Why would nature prefer left over right at all? The standard model describes how the weak force behaves, and it does so with extraordinary success. It tells us which particles participate in weak interactions and how they do so. But the deeper why remains difficult. Why should the weak force be chiral? Why should left-handed particles and right-handed particles be treated differently? This may be a clue to deeper physics, or it may simply be one of the basic facts about how our universe is built. Sometimes science reaches a point where the answer is not yet an explanation, but a carefully measured statement of reality. There is another symmetry that matters here, involving matter and antimatter. If parity is mirror reflection, another transformation called charge conjugation swaps particles for their antiparticles. An electron becomes a positron. A proton becomes an antiproton. A neutrino becomes an antineutrino. Physicists once hoped that although the weak force violates mirror symmetry, perhaps it would still respect a combined symmetry where you reflect the world and swap matter with antimatter. In other words, maybe the mirror world would behave correctly if every particle in it were also replaced by its antiparticle. For a while, that seemed promising, but then nature complicated the story again. Certain weak decays, especially involving particles called kaons and later other particles containing heavy quarks, showed that even this combined symmetry can be violated. The weak force does not treat matter and antimatter as perfect mirror partners in every situation. The difference is small, but it is real, and small differences in physics can matter enormously. This brings us toward one of the biggest questions in all of cosmology. Why is the universe made mostly of matter? In the early universe, matter and antimatter should have been produced together. When matter meets antimatter, they can annihilate into energy. If the universe had created exactly equal amounts and treated them with perfect symmetry, then almost everything might have annihilated, leaving behind a universe filled mostly with radiation and very little matter. No stars, no planets, no oceans, no listeners, and no need for calm explanations about weak interactions. But our universe is full of matter. Antimatter exists, but only in small amounts compared with matter. Something in the early universe must have favoured matter slightly over antimatter. The weak force is one of the places where nature shows that such differences are possible. Its violations of certain symmetries do not by themselves fully explain the matter dominance we observe. The known effects in the standard model seem too small to account for everything, but they are proof that nature does not always treat matter and antimatter with perfect equality. They are cracks in the perfect mirror, and cracks can let in information. This is why weak interactions are studied with such care. A tiny difference in the decay of a particle and its antiparticle may point toward deeper laws. Experiments involving kaons, B mesons, neutrinos, and other particles search for these asymmetries. Physicists measure decay rates, angles, lifetimes, and patterns, looking for signs of imbalance. The goal is not simply to collect details. It is to understand why the universe contains the matter needed for anything to exist. The weak force with its strange preferences may be one of the keys. There is something almost funny about the scale of this question. We are asking why there are galaxies and planets and people, and part of the answer may involve tiny differences in how unstable particles decay. It is like trying to explain the existence of a cathedral by studying the behavior of one grain of dust in the foundation. But physics often works that way. The large is built from the small. The cosmic depends on the quantum. The fact that your hand is made of matter rather than antimatter may be connected, in part, to asymmetries hidden inside weak interactions. The weak force's handedness also connects to the structure of the Standard Model. Matter particles are arranged in left-handed doublets and right-handed singlets under the weak interaction. That language can sound like it was designed to make people close the textbook gently and go make tea, but the idea is manageable. Certain left-handed particles are paired together in the way they participate in the weak force. For example, the electron and its neutrino are connected in one weak family. Up and down type quarks are also paired in weak interactions. The right-handed versions do not participate in the charged weak force in the same way. The arrangement is not symmetric between left and right. This structure is deeply connected to the W bosons. The W bosons can turn one member of a weak pair into the other. An electron can be linked with an electron neutrino. An up-type quark can be linked with a down-type quark. These transformations are not random. They happen according to the weak force's rules, and those rules are chiral. The Z boson too interacts in ways that depend on the particle type and handedness, though its role is different from the charged W bosons. The full pattern is precise, measurable, and central to the Standard Model. One of the surprising consequences is that a mirror image of a weak process may require particles that nature does not provide in the same way. For example, a right-handed neutrino would be needed to make the mirror version behave like the original in certain simple pictures. But ordinary right-handed neutrinos, if they exist, do not interact through the weak force in the usual way. This idea leads into the possibility of sterile neutrinos, hypothetical particles that would not feel the weak force except perhaps indirectly through mixing. Whether such particles exist remains unknown, but the question arises naturally from the strange-handedness of the weak interaction. The weak force opens one mystery, and behind it is another door because apparently the universe enjoys good hallway design. The handedness of the weak force also reminds us that symmetry breaking is not a flaw in a theory. It can be a feature of reality. The world around us is full of broken symmetries. A snowflake has beautiful symmetry, but not every direction in the snowflake is identical. A magnet has a north and south pole, picking out an orientation. A living body is not perfectly symmetric inside, even if it looks roughly balanced from the outside. In physics, broken symmetry can explain why particles have mass, why forces differ, and why the universe took on its present form. The weak force's left-handed nature is one of the most striking examples of nature choosing a pattern, rather than keeping every possibility equal. Still, we should be careful with the word choosing. The universe is not sitting at a desk deciding that left-handed particles seem nicer. The preference is built into the mathematical structure of the weak interaction. It is not a preference in the human sense. It is a rule. But because the rule treats left and right differently, it feels almost personal when we first encounter it. It feels like discovering that the laws of nature have a favourite side of the bed. This can change how we think about objectivity. We often imagine that the laws of physics should look the same from every perspective. In many ways they do. The laws do not depend on whether you're in London, on the moon, or drifting somewhere between galaxies with a very good thermos. But sameness is more precise than it sounds. Some transformations preserve the laws, others do not. The weak force teaches us that mirror reflection is not a universal symmetry of all physical laws. The mirror image of the world may look normal to us, but certain particle decays would reveal the difference. There is a famous way to imagine this. Suppose you wanted to communicate with intelligent beings far away in the universe, and you had no shared reference for left and right. You could describe up and down using gravity, perhaps, or define directions using stars and rotation. But left and right are harder. If you send a drawing of a left hand, how do they know it is not a right hand seen in a mirror? Before the discovery of parity violation, many would have thought there was no purely physical way to define left and right universally, but weak interactions offer one. You could describe a specific weak decay experiment, and the direction in which particles are emitted could define handedness. The weak force gives the universe a way to tell left from right. That is astonishing. A force that operates only over tiny distances and is hidden from everyday experience can define something as basic as left and right in an absolute physical way. Your left hand and right hand still depend on your perspective in ordinary life, of course. But at the level of fundamental interactions, the weak force gives nature a handed rule. It is a small asymmetry with a very large conceptual impact. The Wu experiment and later studies did more than reveal a curiosity. They changed the expectations of particle physics. They showed that assumptions, even elegant ones, must be tested. They also showed that the weak force was not just a weaker version of electromagnetism or some minor nuclear detail. It had its own character. It violated parity. It connected to matter-antimatter imbalance. It involved neutrinos, W and Z bosons, and the deep structure of electroweak theory. It was small in range, but rich in meaning. As we drift through this idea, it is helpful to return to the simple image of a mirror. Look into one, and most of the world still behaves as expected. Your reflection raises the opposite hand. The room appears reversed. A clock face may look wrong if it has numbers, and reading text in a mirror is rarely relaxing unless you are a very dedicated puzzle enthusiast. But the physical behavior of falling objects, light reflection, and ordinary chemistry still makes sense. The mirror world seems possible. Now imagine looking deeper, past the glass, past the atoms, into the weak decay of a nucleus. There, the mirror world fails. The weak force knows the difference. It does not follow the reflected script. This does not make the universe chaotic. It makes it more specific. The laws are not blandly symmetrical in every way. They have structure. They have patterns and exceptions. They allow certain transformations and forbid others. They treat some particle states differently from their mirror images. That specificity is part of why the universe has the form it does. Perfect symmetry can be beautiful, but a perfectly symmetric universe might also be empty of the interesting imbalances that make matter, stars, and history possible. The weak force, then, is not only the force that changes particles, it is the force that reveals nature's strange preference. It tells us that left and right are not always equal in the deepest interactions. It tells us that matter and antimatter are not perfect twins in every weak process. It tells us that small asymmetries may connect to the largest cosmic facts. And it does all of this from a range so tiny that ordinary life never notices the force directly. There is a quiet lesson there. Important things are not always loud, large, or obvious. The weak force acts in a hidden way, but its preferences shape the rules of particle change. Its handedness helped rewrite physics. Its matter-antimatter differences may be connected to why anything made of matter exists at all. Its role in stars and decay ties it to light, time, and the transformation of elements. By looking at the smallest asymmetries, we begin to see why the universe is not just possible, but particular. And now, after following the weak force through radioactive decay, neutrinos, the sun's core, heavy bosons, and broken mirror symmetry, the final question begins to gather naturally. Why does this quiet force matter so much to everything we know? It is weak in name, short in reach, and hidden from our senses. Yet it touches the history of atoms, stars, matter, and the very imbalance that allows a material universe to exist. After following the weak force through radioactive decay, ghostly neutrinos, heavy W and Z bosons, the core of the sun, and the strange left-handed preference of nature, it is worth pausing and asking the simple question that has been quietly waiting behind everything. Why does this small force matter so much? Why should we care about an interaction that we cannot feel, cannot see, and cannot notice in ordinary life? Gravity pulls us to the ground. Electromagnetism gives us light, chemistry, electricity, touch, and the highly specific annoyance of static shocks. The strong force holds atomic nuclei together with immense strength, but the weak force seems almost hidden by design. It works only over tiny distances, appears only in certain transformations, and often leaves behind nothing more obvious than a particle that escapes almost entirely unnoticed. And yet without it, the universe would be profoundly different. The weak force matters because it gives matter a way to change identity. Not just to move, not just to bind, not just to attract or repel, to become something else. That single idea reaches into almost every part of the story we have been telling. A neutron can become a proton can become a neutron, quarks can change type, unstable particles can decay into lighter particles, neutrinos can be produced and sent away as quiet messengers, atomic nuclei can transform into different elements, stars can begin the slow chain of reactions that makes them shine. The weak force is the force of allowed transformation, and transformation is one of the deep engines of reality. A universe without transformation would be a very poor storyteller. It might have ingredients, but not much plot. Matter would sit in fixed arrangements, unable to take many of the paths that lead from simple particles to complex atoms, from atoms to stars, and from stars to the heavier elements scattered through space. The weak force does not do all of this alone, of course. No fundamental force gets to claim the entire universe as a solo performance. Gravity gathers matter into stars and galaxies. This strong force binds nuclei and powers much of the energy released in fusion. Electromagnetism shapes atoms, chemistry, light, and life. But the weak force opens doors that the other forces cannot open. It changes the inner identity of particles, and because of that, it changes what the universe can become. Think back to radioactive decay. In certain unstable nuclei, the weak force allows one kind of nuclear particle to change into another. A neutron may become a proton, or a proton may become a neutron. This changes the balance inside the nucleus. Sometimes it changes the element itself. That is not a small adjustment. It is the nucleus quietly rewriting its own name. Carbon can decay into nitrogen in certain cases. Other nuclei become different elements through weak processes. This is part of how nature moves matter from one form to another over time, not by external reshuffling, but by internal transformation. That ability has given science some of its most powerful tools. Radioactive decay lets us date ancient materials, understand the ages of rocks, study the history of Earth, trace processes in medicine, and examine the structure of matter. It showed us that atoms are not tiny indivisible stones. They have nuclei. Their nuclei can change. Their changes obey rules, and those rules reveal deeper physics. The weak force is one of the reasons a mineral can carry a clock inside it, ticking not with gears or springs, but with rare nuclear transformations that accumulate over immense spans of time. A rock can sit quietly under mountains, under oceans, under desert sand, and inside it the weak force may be helping mark ages far longer than any human memory. This is one of the beautiful contradictions of radioactivity. A single decay event is unpredictable. We cannot say exactly when one unstable nucleus will change, but in large numbers, radioactive atoms create a reliable pattern. The individual event is uncertain. The population becomes a clock. That mixture of randomness and order is one of the signatures of quantum physics. The weak force helps turn probability into history. It lets the smallest uncertain events become the measured record of the past. Then there are neutrinos, those nearly weightless messengers that pass through us by the trillions. They are tied so deeply to the weak force that they almost feel like its signature in motion. They are born when particles change through weak interactions. They escape from the sun, from radioactive decay, from nuclear reactors, from cosmic ray collisions, and from the collapsing hearts of massive stars. They barely interact because the weak force is their main way of touching ordinary matter. This makes them difficult to detect, but also uniquely valuable. A particle that barely interacts can travel from places that light cannot easily escape. This means the weak force gives us a hidden sense organ for the universe. Through neutrinos, we can learn about the core of the sun, the death of stars, and the behavior of particles across great distances. Solar neutrinos confirm the nuclear reactions happening deep inside our star. Supernova neutrinos gave us direct evidence of what happens in the collapse of a massive stellar core. Neutrino oscillations revealed that neutrinos have mass, a discovery that showed the simplest version of the standard model was incomplete. The ghost particles did not merely drift through the story, they changed it. There is a gentle irony in that. The particles that are hardest to catch are some of the ones most eager to tell us secrets, provided we build detectors large enough and wait with enough patience. Neutrinos remind us that the universe is not only visible through light, some of its deepest messages arrive silently, passing through rock, water, metal, and living bodies without drama. They are not loud messengers, they are faithful ones, and their existence is tied to the weak force because the weak force governs the processes that create them and the rare interactions that let us detect them. The sun gives perhaps the most direct answer to why the weak force matters. Every day, sunlight arrives with such reliability that we easily forget how unlikely its source really is. Deep in the sun's core, protons collide in a dense hot plasma. But to build helium from hydrogen, the sun needs neutrons as well as protons. At a crucial early step, one proton must transform into a neutron. That transformation requires the weak force. Without it, the main fusion chain in stars like the sun would not proceed in the same way. The sun would not shine with the steady patience we know. This weak step is slow, and that slowness is a gift. If the sun burned through its hydrogen too rapidly, it might blaze fiercely but briefly. It would not provide billions of years of stable energy for planets like Earth. The weakness of the weak force helps set the pace of solar burning. It helps make the sun long-lived rather than violently short-lived. It helps provide the deep time needed for oceans, continents, atmospheres, and life to develop. When sunlight falls across a quiet room, the warmth feels simple. But hidden in its ancestry is a rare particle transformation made possible by the weak force. So the weak force matters not only because stars shine, but because stars shine slowly. That word slowly is important. Life needs time. Planets need time to cool and settle. Chemistry needs time to become biology. Biology needs time to become forests, coral reefs, nervous systems, eyes, and eventually curious minds wondering why anything shines at all. The weak force helps provide that time by making the sun's fusion process difficult enough to last. It is a cosmic example of restraint. The universe is not only powerful because it can release energy, it is powerful because, in the right places, it releases energy gradually. The weak force also matters in the deaths of stars. In massive stars, weak interactions become crucial as the core evolves, collapses, and produces vast floods of neutrinos. In supernovae, neutrinos carry away enormous amounts of energy from the collapsing core. They help shape the physics of the explosion and the formation of dense remnants such as neutron stars. The same force that quietly helps the sunshine also participates in some of the most violent events in the cosmos. This does not mean the weak force changes personality. It means that the environment changes. In a calm star, weak interactions help regulate slow fusion. In a collapsing core, they help drive rapid transformations under extreme conditions. That is one of the recurring lessons of physics. A rule can be small in one setting and dramatic in another. Water is gentle in a cup and overwhelming in a flood. Gravity is barely noticeable between two apples and dominant across galaxies. The weak force is hidden inside ordinary matter, but in the core of a star or in a particle detector, it becomes one of the main characters. Context turns quiet rules into cosmic events. The weak force also matters because it reveals that nature is not perfectly symmetrical. Its preference for left-handed particles and right-handed antiparticles showed that mirror symmetry is not a universal law. This discovery was shocking because symmetry had seemed so natural, so elegant, so obviously the kind of thing the universe might respect. But the weak force said otherwise. It showed that if you reflect certain particle processes in a mirror, the mirror version is not always allowed in the same way. Nature can tell left from right. That may sound like a detail, but it changed physics. It showed that the universe has structure deeper than ordinary intuition. It showed that the laws of nature are not simply the same under every transformation we can imagine. Some symmetries hold, some break only in tiny ways, but those tiny ways may have enormous consequences. In weak interactions involving certain particles, matter and antimatter are not treated as perfect twins. The known differences in the Standard Model do not fully explain why the universe contains so much matter and so little antimatter, but they show that such differences are possible. They are clues, and clues are sometimes the beginning of revolutions. This is one of the grandest reasons the weak force matters. We exist in a universe made mostly of matter. That fact is so basic that we almost never notice it. Your hands are made of matter. The planet is made of matter. The sun is made of matter. The dust between stars is made mostly of matter. Antimatter exists, but not in equal abundance around us. In the early universe, matter and antimatter should have been produced together. If they had remained perfectly balanced, they might have annihilated, leaving behind almost no material world. Something tipped the balance. The weak force, with its asymmetries, may not be the complete explanation, but it points toward the kind of physics needed. It tells us the universe is capable of playing favourites in subtle ways. Without that imbalance, there would be no atoms to gather into stars, no planets to cool into worlds, no oceans, no cells, no nervous systems, and no one listening to a calm explanation of a force that helped make listening possible. It is one of those moments where the smallest details in particle physics reach into the largest facts of existence. A tiny asymmetry in decay may be connected to the difference between a universe filled with matter and a universe filled mostly with light. The weak force matters because it sits at the crossing point of several deep ideas. It connects particle identity to nuclear change. It connects radioactive decay to time. It connects neutrinos to hidden astrophysical processes. It connects the sun's core to life on Earth. It connects broken symmetry to the mystery of matter itself. It is not the loudest force, but it is one of the most revealing. It shows us that the universe is not merely built, it is allowed to transform. It also matters because it completes the modern picture of fundamental forces. The Standard Model describes particles and interactions with astonishing precision. Within that picture, the weak force is not an isolated oddity. It is part of the electroweak theory, connected at a deep level to electromagnetism. At ordinary energies, the two forces look very different. Electromagnetism is long-ranged and carried by the massless photon. The weak force is short-ranged and carried by the heavy W and Z bosons. But in the hot early universe, at extremely high energies, they were unified in a deeper electroweak interaction. The separation we observe now is a result of the universe cooling and settling into its present form. This means the weak force carries a memory of the early universe. It is part of a story in which the forces we know today were not always so distinct. The universe began in a hotter, denser state where the rules looked different. As it expanded and cooled, symmetries broke, particles gained mass, and forces took on the separate behaviours we now measure. The weak force is not only an actor in today's particle transformations, it is also a fossil of a more unified past, not a fossil made of stone, but a pattern preserved in the laws themselves. The W and Z bosons make this pattern physical. Their heaviness explains why the weak force is short-ranged. Their discovery confirmed the electroweak theory. Their connection to the Higgs field links weak interactions to the origin of particle masses. The weak force therefore sits close to some of the deepest achievements of 20th and 21st century physics. It is part of the road that led to the prediction and discovery of the Higgs boson, and part of the ongoing search for physics beyond the standard model. And there must be something beyond, or at least something more complete, because the standard model, brilliant as it is, does not answer everything. It does not explain gravity in quantum terms. It does not tell us what dark matter is. It does not fully explain neutrino masses. It does not fully solve the matter-antimatter mystery. The weak force touches several of these open questions. Neutrino physics may point toward deeper laws. Rare weak decays may reveal new particles or interactions. Tiny deviations in W boson measurements or flavor-changing processes could hint that the standard model is not the final layer. The weak force is therefore not just a completed chapter of science. It is also a doorway into what remains unknown. That is a fitting role for a force of transformation. Even in science, the weak force changes things. It changed our understanding of radioactivity. It changed the meaning of symmetry. It changed our view of neutrinos. It helped unify forces. It continues to challenge the standard model through precise experiments and unanswered questions. It is weak in name, but it has repeatedly forced physics to become larger than it was before. There is another reason it matters, one that is less technical, but just as important for how we think about the universe. The weak force teaches humility. It reminds us that the most important processes are not always the most obvious ones. For most of human history, no one knew the weak force existed. People saw sunlight, aging, rocks, stars, and living bodies without knowing that deep inside matter, particles could change identity through a hidden interaction. The force was there all along, shaping the world without being seen. Science often advances by learning to notice what was always present but never obvious. The weak force also teaches us to be careful with names. Weak does not mean useless. Tiny does not mean irrelevant. Hidden does not mean unimportant. The weak force is weak compared with other interactions at ordinary energies, but its consequences are vast. It is like a small hinge on a great door. The hinge is not large, and it does not look impressive from across the room, but without it the door does not open. The weak force is a hinge in the machinery of matter. It opens the paths by which particles change, nuclei transform, stars ignite steadily, and neutrinos carry news from hidden places. At the human scale, we live in the outcome of these tiny permissions. Your body is made from atoms whose existence depends on the history of stars. Those stars depended on nuclear processes governed by the fundamental forces. The sun that warms Earth depends on a weak transformation at the beginning of its fusion chain. The elements in the world around you are shaped by cosmic processes where nuclear reactions and decays moved matter through different forms. The stability of matter matters, but so does the ability of matter to change. You are made from both persistence and transformation, and perhaps that is why the weak force feels strangely meaningful once we understand it. It is not just a technical detail hidden in the standard model. It is a reminder that the universe is not frozen. At its smallest levels, it contains rules for becoming. A particle can become another particle. A nucleus can become another nucleus. A star can turn simple hydrogen into helium and later help seed space with heavier elements. The story moves because change is allowed. Now, as our quiet journey reaches its resting place, we can look back at the weak force with a little more respect than its name first invites. It is short-ranged, but it reaches into the history of stars. It is weak, but it helps regulate the sun. It is hidden, but it reveals itself through radioactive decay, neutrinos, and particle transformations. It is strange, but its strangeness is measured, tested, and woven into one of the most successful theories humans have ever built. It is asymmetric, selective, and deeply specific. It does not do everything. It does something no other force can do in quite the same way. It changes particles. And from that change comes so much more than we might have expected. The glow of stars, the clock inside ancient rocks, the ghostly rain of neutrinos, the imbalance between matter and antimatter, the possibility of elements shifting over time, the evidence that nature knows left from right, the clues that our deepest theories are powerful, but not yet complete. So if you remember one thing from tonight's journey, let it be this. The weak force is not weak in importance. It is weak only in reach and strength compared with some of nature's louder forces. Its influence is quiet, precise, and hidden at the smallest scales. But the smallest scales are where the universe writes many of its most important rules. And when those rules are allowed to unfold across stars, atoms, planets, and time, the results become everything we know. If this journey has helped the strange world of particles feel a little calmer, a little clearer, or simply a little more wondrous, I would be grateful if you gave the video a like and maybe subscribed. It helps this quiet corner of science reach others who might enjoy learning gently without hurry as the universe slowly settles into view. And if you're listening late at night, perhaps with the room dim and the day nearly finished, take a moment to notice how still everything seems. The walls, the air, the soft weight of the present. It all feels steady. But deep beneath that steadiness, particles follow their hidden rules. Some remain, some change. Some send out neutrinos no one will ever catch. Some help stars shine across empty space. The weak force is there in that hidden world, quiet as ever, allowing matter to shift just enough for the universe to have a history. And somewhere in that history for a little while, there is this moment, this breath, this small pause in the long transformation of everything. Sleep well, fellow traveller, wherever you are, and let the quiet forces of the universe carry the story onward.